AI and Quantum Computing, the Future of Intelligent Systems. We are on the final day of this FDP program. Already, we had a session at 11 a.m. due to certain inconvenience which has not yet been occurred yesterday. So now we are having three very intensive and informative sessions. Already there were 10 very intelligent sessions covered so far. We had two international speakers also with us. So let's not delay any further. Let's welcome Dr. Anish Chivukula from BITS Pilani Hyderabad campus. But before welcoming him, let me brief about Dr. Anish. Dr. Anish Chivukula is the assistant professor in the Department of Computer Science and Information Systems, BITS Pilani Hyderabad campus. He has an enlarged work experience of R&D with 4.5 years, in academia of 4.5 years, as well as in industry of 7.2 years. His educational qualifications include PhD in data analytics and machine learning from University of Technology, Sydney, Australia, MS from IIIT Hyderabad, and BTech in EC department from JNTU Hyderabad. He also has supervised undergraduate project students, undergraduate thesis students, as well as master's project students. He has delivered the online program management of the short courses like Applied Data Analytics, Data Analytics Foundations, and Advanced Data Analytics on a rolling basis. By sharing best practice around data analytics, innovation, and commercialization, he provided thought leadership in the micro-credential stackable degrees offered by UTS to Australian corporations such as Telstra to meet the demands of digital and technology service businesses, as well as in international collaborations such as with the Open Cyber University of Korea to satisfy hybrid study modes. He has written a research monograph on adversarial machine learning published by Springer Nature. So let's welcome Dr. Anish Chivukula for his very enriching and informative session.
Good afternoon. Am I audible?
Yes, sir, you're audible.
I have shared the screen. Are you able to see the presentation?
Yes, sir.
Okay. Yeah. So good afternoon, everyone. We'll be discussing about quantum machine learning in this talk. So I have created slides into several components. One is what is quantum computing, then how is it useful for machine learning, what is machine learning, and what are the algorithms used in machine learning, and how quantum computing can be leveraged for such machine learning algorithms. I've also tried to summarize some of the research directions in this area. So if we finish early, we can have an open Q&A session. Otherwise, please drop your questions to the organizers and then we can take them offline. So quantum computing is an area based on quantum physics, and it offers a new hardware platform where classical computing paradigms, such as the systems, algorithms, applications which are developed in a computer science department, can be deployed on a quantum computing platform. Now, this platform can be thought of as a new computer, which is a counterpart for the classical computer based on von Neumann architecture. So if we, for example, take algorithms as an example, for how they are implemented, designed, analyzed on a classical computer, and what would be the variation in their design and analysis for a new quantum computer, that will be a way we can approach quantum computing from a computer science perspective. Quantum computing is based on properties of subatomic particles studied under quantum mechanics. And in terms of a quantum computer, we have to represent the information used in the algorithm in terms of the bits and operations which we can perform on the bits suitable for programming on the bits in the computer. So we have to think in terms of bits, which will be mapping to particles in the physics domain. In quantum mechanics, there are two properties called superposition and entanglement of subatomic particles, which are leveraged by us to make bits acting as a building block for a quantum computer. Also, classical computers, such as in a C program, perform sequence of operations in a deterministic way. That is, how many ever times we run the program, we get the same output from the program, provided the input is fixed. So suppose we run the program for 100 times. It is not the case that in the 60th run, we get a different output from what was the case in the 30th run. So for a particular input-output combination, the sequence of operations which are performed on a classical program will give the same output across different executions of the program. But this is not the case in a quantum computer, where depending on the physical properties of the system, every time we run the program or we do some operations on the quantum bits, the result obtained will slightly change. And there is a probability associated with the result obtained. So we'll have to check whether the result is according to our expectation, or if there is error in the result, which has to be further reduced. Based on such criteria of deterministic versus probabilistic programs or bits versus particles, quantum computing introduces a new world to us, where all the existing algorithms, and specifically the machine learning algorithms, must be implemented in this new world. So there are certain components of machine learning, such as optimization, simulation, encoding, which are ported onto the quantum computing device or computer in such a way that the machine learning gives expected results with reduced error. From a machine learning perspective, this will be our goal. Whereas from a quantum computing, quantum physics perspective, there are certain other physical phenomena which must be accounted for when we develop the algorithms. And right now we are focusing on superposition and entanglement, which are the physical phenomena helping us create a quantum bit. Now we know that in a, let's say, a workstation, in the random access memory, the data is stored in terms of bytes, and 8 bits make up a byte, and every bit can take a value of 0 or 1, but no other value. So either it has a value of 1 or it has a value of 0 and no other value. And the sequence of such values will decide the byte and then the data type of variables which are stored in the memory. And then we can either do bitwise programming on the bytes, or we can do higher level application and system programming on them to create, let's say, a C program. And then we think of several application areas of such a programming paradigm. But in a quantum computer, as illustrated in the figure, the value which the bit takes can be a fraction between 0 and 1. And that value, for example, 1/3, is expressed in terms of a combination of particles representing 0 and 1. And if we have to represent the data as we are habituated to in terms of bits and bytes for a quantum computer, we'll have to use matrix algebra. And every particle will be able to encode a vector of values in it. So instead of using many bits and bytes to encode an information, like let's say a data type of a floating point number, into the main memory of the computer, we can use a reduced number of bits. And I have created a table where there is a mapping between what sort of reduction is possible with a quantum computer. And essentially, we are able to use very few bits and create a vector representation of the data and scale the solution for very complex algorithms, such as cryptography algorithms. And here, there is a quantum mechanical bit represented as a vector. And this corresponds to a subatomic particle whose properties such as amplitude, spin, mass, position, etc. are represent the 1 and 0 values in the vector, which is used further for machine learning. And this is the phenomenon of superposition, where a bit can take several values at the same time, rather than a single value of 1 and 0. For example, if the particle is pointing upwards, it corresponds to 1. If it is pointing downwards, it corresponds to 0. But what if it is pointing at an angle? In classical computers, this is an error, and there is no representation for this in the memory of the computer. Whereas in quantum computers, an angular particle is represented in terms of a summation over the vectors 1, 0 and 0, 1, taking some weights C1 and C0, so that any orientation of the particle can be expressed in terms of the C1 and C0. And these vectors 1, 0, 0, 1 act as a basis vector space for a matrix representation of the data. Therefore, instead of 1 and 0, we will have a vector 1, 0 and vector 0, 1. And the data which we want to represent will be a linear combination of these vectors. This is the difference between a quantum bit and a classical bit. Therefore, using the physical property called superposition, the information which we want to encode into the algorithm can be represented in terms of basis vectors spanning a linear algebra space whose weights determine the information content in the data. And this space is called the Hilbert space in physics. It will be a search space for the machine learning, where the data is represented as a sample in the search space. There is also a probability associated with this representation, where it is not guaranteed that the data has been represented in the subatomic particle and the quantum bit with 100% guarantee. There is a chance that some of the bits may be switched on with more probability and some of the bits with less probability when we map the data to the quantum bits. So we look for those bits which have higher probability. and map to the algorithm which is solving the problem at hand. Now the bits are used to create logic gates in the computer, and this corresponds to the state functions in quantum mechanics systems, where several events which are happening in physics are associated with the probability of their occurrence. And several quantum mechanics states express these events. These states correspond to the output of the logic gates like AND, OR, NOT, XOR operations which we do on the bits in machine learning. So there is a probability function associated with the data in a quantum bit. And this superposition principle is related to the wave particle duality phenomenon seen in quantum physics, where wave particle enables the information to be encoded into a vector, and the particle property enables to identify the probability associated with each element in the vector. And this is the Schrodinger wave function associated with every particle, and we are leveraging it to create a bit representation of the data, but with a probability. And as we keep increasing number of bits, for example, we have 200 bits, which are quantum bits. Are they the same as having 200 bits in the main memory of the current computers? Here, because we have a vector representation of the data, whereas in the current computers, we have a scalar representation of the data. The data can be encoded in a much more compact manner into the quantum computer. And as we increase the number of bits in the quantum computer, the amount of data which can be encoded into it has an exponential advantage. That is, if we have, say, 8 bits in a computer making a byte, we only require 3 quantum bits in the quantum computer. And if we have, let's say, 1024 bits in the main memory of the current classical computer, we only require 10 bits in the quantum computer. So as the number of bits keeps increasing, so let's say there is a quantum computer with 300 bits, it can represent a very, very large number of the order of 10 power 90. That is, there are 90 zeros after 1 into the 300 bits of the quantum computer. Thus, there is an exponentially added advantage for us to use a quantum computer in developing algorithms. However, due to principle of entanglement, every component or every particle in a quantum computing system or a quantum physics system is related to every other particle. So the information content encoded in one particle affects the information in another particle. To be able to design a computer that is able to perform operations on the bits, we must isolate the set of particles into which we are encoding the data from the remaining particles in the quantum physics system. And this is a difficult problem. It cannot be done. This isolation cannot be done 100%. There will always be some noise caused by the other particles into which we are not encoding the information. And we want to perform the computation subject to the noise, such that we want to leverage the exponential added advantage provided by the quantum bits. At the same time, we want to get the algorithm output with less effect of noise. So this is one challenge due to entanglement of the subatomic particles that is to be addressed in a quantum computer. Now, assuming there is a system which is able to give us such kind of a representation of data in a very compact manner in terms of linear algebra matrices, let us see how machine learning algorithms will be built on such a system. So for that, we have to understand what is a machine learning algorithm. How is it different from a normal algorithm? So here's an example where all of us know how to add two numbers, and we follow the decimal number system to do that. Earlier, before say Aryabhata's time, there was the Roman numeral system which was being followed, say in accounting, let's say somewhere near Dubai. But with the introduction of decimal number system, new algorithms were discovered on the numbers 0 to 9, such that very large numbers, such as credit and debit, balancing the books in an accounting problem, can be expressed in terms of the decimal numbers. So starting from that time onwards, we have an algorithm to add numbers in the decimal notation. For example, if we add 9 with 1, there is a carryover of 1, and the result is 0. And digit by digit, we are able to do the addition operation. And we are able to do this for very, very large numbers or very, very small numbers, or the kind of numbers which occur in the real world, such as in a finance application. Now, given such a search space of numbers, we know as humans that we can add, let's say, a 3-digit number 189 with 2-digit number 11 using a certain algorithm. And we empirically execute the algorithm to come up with the result 200 on the right hand side of the equation. Similarly, if we have to add up a number 2 with 10 factorial, we know that 10 factorial has to be expanded into a very large number, and then a relatively small number 2 has to be added to it. So when somebody says that the result of this addition is 198, then we know clearly that this is false, because we know 10 factorial is a very large number. It is much more than 198 or 200. Just because the previous calculation 189 plus 11 led to the value of 200, we know that the current calculation 2 plus 10 factorial will not lead to a number somewhere close to 200. So we know that the first equation is true or right, and the second equation is wrong or false. Similarly, we can take any two numbers and keep adding them to create a left-hand side and right-hand side of the equations. As we keep getting practice with such numbers, we are able to evaluate whether the resulting number out of the calculation is right or wrong, true or false, very quickly, without actually doing the calculation also, based on some approximations. Also, we are able to generalize our knowledge to addition of two new numbers, 99 and 101, based on the algorithm which we have learned previously. This is what human intelligence is doing. Now, when we want to put this into a machine meaning a computer here, either a classical computer or a quantum computer, we have to think of the problem in terms of data and build the algorithm on the data. For example, 189 and 11 are two instances of attributes representing two numbers. And 99 and 101 are two other instances. The job of the machine learning algorithm is to give the result of adding these two numbers. So it has to learn the concept of addition in the decimal number system. And it has to, when given a test data such as 99 and 101, it has to give a result which is correct. If it is giving a result which is wrong, then we will not use it. We might as well do the calculation manually. We already know the algorithm. So why should we use a computer to implement the algorithm? We know the algorithm, but suppose it is a very, very large number or it's a very small number. Then it will be tedious for us to implement the algorithm. Such as, for example, Chandrayaan-2 has gone to the moon. And there are so many maneuvers which are made in the orbit to leave the Earth and then enter the moon's atmosphere and then land on the moon. All these calculations around how the maneuvering should be done in the space, if we start doing it manually, it will be very tedious. And this has to be done in real time. Let's say every minute or every second. So although we know the algorithm, it will be, we don't like to implement the algorithm on many data examples. Like we don't want to do the calculation every minute, every second to do the maneuvering to leave the Earth and arrive on the moon. That is where a computer will automate our thought process and create a program implementing the algorithm. And the algorithm will be data driven. So we have to provide data to the computer, such as how to represent numbers in the computer and what is the concept like addition, which the computer has to learn. And that concept must generalize to new test examples in which correct result must be obtained. Now, how to design a C program or an algorithm to do this? That is the challenge of machine learning. So we must create the data, we must know the concept, we must write a program to map the concept to the data, and the model which is learned through the machine learning algorithm must generalize to new data. Data, concept, examples are all coming from the environment. Now, how to formulate the problem in this case to build an algorithm which is able to intelligently learn some patterns and map them to the concepts which we want to verify. That is the challenge of machine learning. And one way to do this is using the target function concept in the probably approximately correct framework used in computational learning theory, where, for example, a customer goes to a bank and bank has to decide whether to give a loan approval to the customer or not. And bank will do this by looking at historical data of all its customers and what kind of loans were given to all such customers, and then put this new customer into one of the categories of the previous customers, and based on that give an estimate about whether this particular customer will repay the loan or not, and based on that give a credit score to this customer, which will appear as an output of a software to a bank manager who will finally approve the loan. But in a machine learning algorithm, this will be mapped into data xi, yi ranging from 1 to n. So there are n examples which are mapping a function f from the domain of x to the domain of y, such that this function is the credit score function, which is learned by a machine learning algorithm, searching through several hypotheses for what could be this function. For example, this could be y equal to x squared, or this could be a polynomial function, or this could be a linear function, or it could be y equal to sin x by x. Similarly, it searches through all possible candidate formulas for what the function is. And for any given record of a particular customer called X, there will be a output Y, which will be produced by the model, output by the machine learning algorithm. And this model will learn a function G, which is an approximation of F, because we have limited set of data. Only n examples are there. That is the n customers which are there in the bank. We are able to find some pattern and map to the new customer. But what if there are 2n customers, 3n customers, and many more data points available for learning the function? Is the function going to be better in that case? What is the effect on the error of the function? So based on considerations like this, we say that machine learning model is learning an approximate mapping from the X to Y, and it can be approximately used to come up with the credit score for the customers. Thus, given a data set, we are able to map it to a learning algorithm, which is automatically learning patterns like the functions f and g here, based on some search and optimization conditions, which is the algorithm. Another way to think of this is, suppose we have to detect a cat apart from a dog. How will we get the main parts of the image representing the cat and dog, like the eyes, nose, and mouth of a cat, and then decide whether the eyes are that of a cat or that of a dog? This is the job of machine learning, where we have to first remove the background of the data, like background in a picture taken of a cat. Maybe the cat is on a tree, so that tree information is removed from the image. And then the face of the cat is focused on, where the eyes of the cat are isolated. Then all possible cats in the world and their eyes will be stored in a database. And they will be compared with that of the current cat to decide whether it is a cat or a dog. And the decision model is the logistic regression model, which gives the output label. Like given the input camera image of a cat, the output label could be, this is a cat. Or it could be, this is a dog. Thus, there is a lot of data preparation required for building the machine learning models. And then we have to select which is the best model for the task at hand. And it has to satisfy our expectation on the performance of the algorithm. If it is giving wrong output, we will not use it. So it has to be performant, very highly performant. 95% of the time, it should give the right answer. Therefore, machine learning is the study of algorithms, such as normal algorithms, solving a problem, where there is additional requirement that the algorithm should perform according to a performance metric P for a particular task T, like classifying cats and dogs, and it should be based on data E. Therefore, PTE are three different mathematical terms which the machine learning algorithm must satisfy, along with the regular algorithmic properties like time complexity of the algorithm. Now, several such algorithms can be put into a workflow, such as there could be a training algorithm, a test algorithm, validation algorithm, and all of these are machine learning algorithms which will work on raw data to come up with a model on training data set, which will be evaluated on test data and fine-tuned on validation data, such that the raw data has been processed into an output which we can consume, and it is according to our expectation. For example, look at this puzzle, where there are black and white squares on the top and bottom. Then there is a new combination of black and white squares. Now, to think in terms of the machine learning algorithm, we have to understand the pattern which is learned by the algorithm for the black and white squares on the top and how it maps to the pattern for the black and white squares on the bottom. So for example, if the prediction of the model is -1 on the top and +1 for another combination of squares, then what could be the prediction here? This is how the computer thinks. Computer is a machine, it only calculates. But if you have to associate a thought process for the computer, then this is how we should think of it. And for example, you can say that there is some kind of a connected component pattern in the second part of the figure rather than the first part. So the output is +1 in the test case in the bottom part of the figure. But you could also say that just look at the first square, and if it is black, then output is -1. So since the first square is black in the test case, output is -1. So the question is, which is the right answer? Is it +1 or -1? It depends on what pattern we are looking for in the data. So it is a chance. Answer could be +1 or -1, subject to some conditions in the data. So you can see that this is not how humans think normally. But when we try to build a machine learning algorithm, we have to consider such uncertainties and probabilities in the output. And such probabilities will directly map to the quantum computer, such as coming from the wave particle phenomenon. The way I have presented the machine learning problem to you is based on algorithms, which is the computer science perspective. That is, problems are defined in computer science and we have to build an algorithm which will solve the problem. But the same machine learning algorithms or model can be defined from other disciplines perspective, such as from statistics perspective, where we have to think about the assumptions made on the data and the mathematical model which is built subject to those assumptions and whether the mathematical model is useful. Or from economics perspective, where there are several participants in a market, like in a vegetable market, where if we go to the vegetable market, some vendor is selling vegetables. So we have to decide which vendor to go to. So probably we decide that based on whoever is offering the lesser price. Or probably we go to the same vendor again and again every time we visit the market. And that vendor gives us a discount. Or probably it's a wholesale vendor. So based on interactions in the market, mechanisms, economic mechanisms such as price are set. And there is an optimum solution for such a price based on several parties interacting in the market. Now suppose the vendor increases the price a lot. Then government intervenes and then says that it cannot be increased beyond a certain threshold. So the government's job is to ensure that we get all of us get vegetables at a reasonable price and inflation doesn't affect us. So there is a concept of a common good, which is also included into the market interactions. Now, machine learning algorithms can also be defined in terms of this. And similarly, there are many other disciplines, including physics, in terms of which we can define the machine learning algorithms. I have written one more point on electrical engineering, where a control system framework can be used to define machine learning algorithms. Now, we have to map this to the quantum computer. And we should be able to get predictions or outputs from the model based on some patterns learned in the data, which are useful predictions. And we want to build the model in a reasonable amount of time, such that the predictions are according to our expectation. So the model should generalize to new data, such as in the adding numbers case. But at the same time, it should be able to encode patterns from the current data. This is called the overfitting underfitting condition in machine learning, where we want a model that is neither too complex nor too simple, but just right for the task at hand. So it is a simple model, but it is not a simplistic model. It is not a very complicated model, but it is just the right model. This we measure in terms of some statistical errors, such as training error, validation error. And based on comparisons between these errors across different runs of our program, we are able to draw conclusions empirically on whether the machine learning model we have built is a good model or a bad model. And this leads to different kinds of machine learning, like supervised, unsupervised, reinforcement, deep learning, so on. So I've given some tables here, which will help us understand the comparison, pros and cons between different kinds of machine learning algorithms. Most common paradigm for machine learning is supervised learning. Most common example for which is classification. But there are other kinds of models, such as regression models, where the job, like in the bank credit score case, is to give a prediction score for a particular input record. And already previous mappings of the scores are available in a database. If they are not available and only input records are available and we have to explore the data, then it is unsupervised learning. If partially some of the labels are available and partially they are not available, then there are variations of supervised learning like semi-supervised learning, self-supervised learning. And for each of these problems, there are several models which are built, such as decision tree, support vector machine, random forest, neural networks, deep learning, etc. Each of these models have several applications, such as in recommender systems on YouTube or fraud detection in banking or robot navigation with reinforcement learning. Thus, several kinds of machine learning algorithms can be used to create different types of models having several applications in the real world. When machine learning is combined with mathematical models, then we get deep learning. Here are examples of several models, such as the recurrent neural network, convolutional neural network, deep belief network. These are all different neural network architectures useful in several tasks in the applications. They can be contrasted with other techniques like statistical techniques based on the Bayesian paradigm in statistics, starting from the naive model, or they can be compared with other kinds of machine learning algorithms like reinforcement learning algorithms, which are driven by a reward rather than a class label. This slide explains the concept of reinforcement in reinforcement learning, where there is an AI agent or machine learning algorithm which is taking an action. We can think of it like two players playing a chess game. So every player is able to observe the other player's moves, and based on that, they are making the best move, which will help them win the chess game. And each player can be thought of as an agent, and they are taking an action which will lead to change in the configuration of the chess game from one state to another, and it will give a reward for each player or agent. And this reward is coming from the environment on whether they will win the game or lose it. And several such sequences of rewards will finally decide the final optimum solution of the machine learning model. This is a different way of thinking from the normal supervised learning paradigm, which is very common in machine learning. So we have to define what is a reward, what is an action taken by the agent in the environment, and what is the transition which happens due to the action. And several other similar variables must be defined in the machine learning algorithm. This is a taxonomy of some of the existing reinforcement learning algorithms based on such definition of variables, search spaces, parameters, and outputs. For example, there are on policy and off policy methods for reinforcement learning, which are called value-based methods. And model-based deep reinforcement learning methods are compared with or contrasted with model-free deep reinforcement learning methods. So model-based ones make some statistical assumptions about the data, and they are very mathematically driven, whereas model-free ones are data-driven. Therefore, we can see that there are several terms associated with machine learning, and we must find a way to organize all these terms. One way to do it is using mind maps. So we put these terms into different categories, such as whether it is technique or application, theory or practice, which type of algorithm are we talking about. And these mind maps can be mapped to particular application areas like time series forecasting in stock market data, recommender systems on YouTube, user segmentation analysis in marketing, so on. And depending on the application scenario, we can decide which is the best model to build for machine learning and apply it for the given data set. But when we try to build the algorithm itself, based on which the model is being built, then we have to understand how the data is being represented in the algorithm, which is called feature selection. And then we have to understand what is the best model which is built for a particular class of algorithms, which is called model selection. And these are the two major steps in pattern recognition, which is one of the approaches to take to build machine learning models. Here there is a diagram showing how pattern recognition algorithms are built for classifier design. In the interest of time, I will not go into the details of this diagram. Here there is another diagram where again classifier design is being done in a pattern recognition framework, but there is some feedback loop coming from the output of the classifier according to which the classifier is being fine-tuned. There are several feedback loops here. This is one loop, this is another loop, and then this is another loop. So based on these loops, we can fine-tune the algorithm. This is a statistical mathematical way of understanding the same idea, where the search space of the training and test data should be same, and the model which is built on training data should generalize to the test data based on some probability calculation, which results in a score associated with the prediction supporting the decision output by the model. In a more practical sense, such as in software engineering system, machine learning can be part of the project lifecycle, which is built for a larger goal, and it is driven by data. So we should be able to process, collect, store, etc. data, and then train, extract, optimize, etc. the model, and then package, test, develop, etc. the result of the modeling, and then operationalize the results for different real-world applications, such that we are able to monitor the outputs from the model and validate whether they are according to our expectation, and have a release cycle on whether the outputs can be improved in some way by improving the data or algorithms or the development life cycle, so on. This is a more practical way of thinking about machine learning. And one application of this is in data mining, where focus is more on understanding the data and finding patterns in it, such that well-prepared data is available for the machine learning models, and it is useful in the application. So there are 6 phases according to the CRISP-DM model, which is shown here, cross-industry standard process for data mining. And each of these 6 phases have further reference architecture checklists, which we can use to build the best model for the given task at hand. So all those slides were describing how do you build a machine learning algorithm, and what is the kind of thought process which goes on behind how to understand patterns learned by a computer. But when we think of the problem, we simply look at the data, such as in images, and we are able to do the task, such as classify the images. For example, if we show that this is a plane and this is a bike, then we'll have to classify and distinguish or differentiate between how to tell this is a plane and how to tell this is a bike. For example, we could say that this plane is moving. How do we know it is moving? Because it is in the sky. Whereas bike is not moving. How do we know it is not moving? Because it is parked. There are 2 wheels to a bike, whereas to a plane, there are no wheels. So how is the plane moving without wheels? Because it is moving in the air, whereas bike is moving on the road. So like this, we can come up with several descriptions of the images or data presented to us and make the classification or differentiation between the objects present in the images. We are able to do this instinctively and in a very short amount of time. However, the problem is, if we are presented with thousands and millions of such images, we would not like to perform the task of classification on such images. Right? So for example, all the planes in the world and all the cats in the world, if we have to tell the difference apart from each plane and each cat, then it is a very, very tedious job for us and we don't like to do it. But the computer requires such amount of information. It requires many, many, many images of cats to learn patterns about the cat, like eyes of the cat, and then use that information to classify a cat apart from a plane. Now, the examples which are shown in this figure, we can easily make out the difference between these examples. But if the same cat is used in context of other examples shown in this figure, for example, take this cat and this. Is this a cat? Or is it a dog? Or is it a tiger? It's probably a cheetah. So if it is a cheetah, how is a cheetah different from a cat? So we cannot say that there is a road, there is a sky, there are tires, and some object is parked, some object is moving. So we cannot use any of that information here. And if we say cat has 4 legs, cheetah also has 4 legs. If we say cat has 2 eyes, cheetah also has 2 eyes. So what is the distinguishing characteristic between these two images? For example, we can say this is a painting and this is a real world photo. How do we know that? Because of the background. So we have to look for more nuanced and specific characteristics of the data, which will help us do the classification. Hence, this problem is a harder problem for us, and similarly for the computer. And there is also example here shown of a dog and a wolf. So we can probably tell a cat apart from a wolf, but it'd be hard to tell a dog apart from a wolf. So by looking at the background, we can tell that this is a dog in somebody's house, whereas probably this wolf is in the wild because there is probably another wolf in the background. So based on such additional information, we are able to tell whether this is a dog or a wolf. However, as humans, we are able to do this calculation instinctively in a very short amount of time. Whereas for the computer to learn this kind of a nuanced approach to distinguishing between images requires a lot of data and a long amount of time. So for the computer, this is a harder problem than this. Hence, we should be able to create neural network architectures in deep learning which address such problems. We are able to do that by mapping input with output based on a function and a network architecture, which is like a graph for the neural network. And we go through several steps to optimize these functions. We have to first design the function, then we have to decide what is the machine learning technique or algorithm used to solve for that function. Then we have to design the neural network architecture and then pick the optimization algorithm which will solve for the best solution. So in all these steps, we have to make design choices on what is the best neural network. Some of the choices are given here based on the task at hand, like whether it is classification task or ranking task or detection task, etc. We can ask questions such as, how is Y mapped to X? Are we looking for Y that is most compatible with X? Or are we looking for Y1 and Y2 which are more compatible with X? Or are we looking for a particular value of Y which is compatible with X? Based on questions like this, we'll have to design the neural network. Once we have designed the neural network, the workflow which we follow to implement the program will look like this, where we have to create a class of the neural network, like a Java class or a Python class, and get a model instantiating the class. Then we have to decide the functions used subsequently in the iteration, optimizing for the parameters in the neural network, such that the input maps with the output and arrives at an optimum solution. These are some of the neural network architectures which are common, such as autoencoders, convolutional neural networks, generative adversarial networks, so on. These can be mapped to several machine learning paradigms like supervised, unsupervised learning, and they are suitable for different kinds of problems based on the data and scenario in which the application is working. And we can come up with several design choices among these neural networks. Some of the most common applications, such as in networking applications, are given in this slide. Thus, we can think of machine learning as composed of supervised, unsupervised, and reinforcement learning. Among supervised learning, there are tasks such as regression classification tasks, which can be solved either with traditional machine learning algorithms or new deep learning algorithms. And these have to be mapped to the quantum computer to give their quantum versions or variations of such algorithms. We can also think of the workflow which is used to prepare the data for these algorithms, and several algorithms which are put together like learning and inference algorithms in this workflow to come up with the final score of prediction. Thus, deep learning is a part of machine learning, and machine learning is part of AI. So our task is to come up with AI which works on the quantum computer. There are several packages available, such as in Python, to implement all these models, such as PyTorch, and they give several features for the programming convenience. We would require similar tools in the quantum computer case. And similar to how we are mapping several classical machine learning algorithms to the deep learning neural network architectures, we would have to map the machine learning models to the quantum computing models. These are some of the advantages that deep learning offers over machine learning, such as features are automatically extracted by the deep neural networks, and a lot of manual feature engineering is not required to build the best model. Similar advantages, such as performance gain obtained due to exponential performance of the quantum bits, are advantages offered by quantum algorithms. These are some of the neural network architectures which are commonly used. For example, this is a CNN architecture where the convolution operation is performed on the images, and several such convolutions are summarized in the max pooling operation to come up with a fully connected layer giving the prediction of interest. Such architectures have to be built, that is, quantum neural networks must be built in the quantum domain. This is the workflow followed for including all these deep learning models into the project lifecycle which we have designed. And this includes pre-processing, in-processing, and post-processing stages, where pre-processing creates the data or the training data for the neural networks. And in the in-processing stage, we have to decide whether we are doing supervised learning or unsupervised learning, so on, and map it to deep learning paradigms like discriminative learning, generative learning. And then we have to decide what is the application task at hand, and the neural network architecture should solve for that problem. Then build the model, then decide it is the best model according to a statistical performance analysis, and also domain knowledge on what we are expecting as output from the model. Now, all these workflows should be mapped to the quantum computer also. Simply doing addition of two numbers using qubits will not suffice. And we have to build machine learning algorithms on such a computer, going beyond traditional algorithms. where there could be no learning component. So we can make a distinction. We can distinguish between algorithms and learning algorithms. Adding two numbers, how to do that is an algorithm. But how to use it in an AI application is a machine learning algorithm. So the learning component of such an algorithm must be supported on the quantum computer. Therefore, quantum computers make use of superposition principle and have a vector representation of the data, which significantly improves the runtime of the algorithm. And most of the quantum computers, quantum algorithms are able to exceed performance of the classical algorithms which are there, such as in cryptography case. All the cryptography algorithms have been broken by quantum algorithms. How will this translate to machine learning case? Such that there is some AI built into the machine learning algorithm and it is able to work on the quantum computer. So we must think about the advantages offered by quantum computing, such as exponential speed up, and think of how to make improvements to the machine learning algorithms, such as representing data using linear algebra. So here is an illustration of quantum bits which take only two possibilities, classical bits which take two possibilities, compared with quantum bits which are represented by a sphere, and any point on the sphere is a possibility for representing the data as a matrix, or in general a tensor. And we should be able to build algorithms on the qubits such that they have minimum error rate and they are able to solve the problem at hand. And the problem at hand could be a classification problem, clustering problem, supervised problem, unsupervised problem, etc. And depending on what errors come up due to that problem, we are able to decide what is the minimum error rate acceptable for the problem at hand. At the same time, the error is also coming from the quantum physics system, which we have to optimize. Thus, we have to find parameters which are close to the initial values of the optimum solution, or we have to reduce the complexity of the algorithm so that the time complexity reduces. Now, how do we address these challenges in terms of quantum bits and quantum computer? This is the research question for quantum machine learning. So this is a repeat of the previous slide where we saw that any given data can be encoded using the Schrodinger wave function into quantum bits. And then several possibilities are there for the values which are stored in the vectors representing those bits. Those possibilities will be used to make and or not sort of gates in the hardware implementing the computer. And here there are several such gates which are shown in terms of several operations performed on the quantum states. For example, we want to implement the XOR gate, and this has to be mapped to the bit level, quantum bit level, using these matrices. And these are the physical hardware representations of the circuit implementing these matrices. Combination of these matrices will give us the result which we are looking for. That is, we want to encode data into these matrices so that very few quantum bits are required to encode lot of data. And then we want to process all these matrices in the machine learning algorithm. Earlier, the process was based on one record at a time. Now the process will be based on several matrices given as input and several coming as output, similar to a parallel algorithm. Therefore, be able to create algorithms on a quantum computer, we must be able to use the gates coming out of the quantum bits to create several quantum states on the input and output, and create algorithms that are probabilistic, so that across several executions of the algorithms, we are able to get the desired result on the output of the algorithm. And till now, we have been encoding the data into the Hilbert's search space and using it as a starting point for the algorithm. Subject to these assumptions, we will see what are the bottlenecks in the machine learning algorithms which can be addressed using a quantum computer. If this is a classification problem, and we have several training examples, representing the attributes of the data and used to make some prediction on the class level, then if the number of attributes is very, very large, such as an image classification task, if we have to classify all the images of different categories, and there are millions of images in each category, then what are the attributes used to summarize those images and compare them with other images? How many such attributes would be required? If we end up with a large number of attributes, then a quantum computer, because it is able to encode data in a very compact manner, is able to deal with these large, very, very large, like millions and billions of attributes. And right now, with the existing computers like a workstation, that is not possible. In case of clustering, if we want to partition the data into several partitions, and then think of each partition as a cluster, then what is the best configuration for the partitions is an optimization problem, and quantum computers can solve such a problem using quantum bits. There are several other algorithms, such as in pattern recognition, optimization, probability theory, which can benefit from quantum computers. Some of the approaches to leverage quantum computers to build such algorithms are listed in this slide, where we can see that representing data, there is an advantage offered by quantum computers. There is an advantage offered in terms of the probabilistic output which is coming from the quantum computer, and also in terms of the computational complexity of the algorithm, and several other theoretical directions from information theory and probability theory. However, there is need for a lot of R&D in this area. That is, we have questions such as how to implement best optimization technique for a given machine learning model on the quantum computer, how to include information such as distance metrics used in clustering into the encoding of the quantum computer, how to formulate an output from the machine learning model such that quantum physics information is included in such an output, and then overall, how is quantum computer able to speed up the calculations in the machine learning algorithm. There are several proposals and several approaches to address these questions in the literature, such as use the quantum computer as a hardware platform and build probabilistic models, machine learning, which will leverage the quantum computer. Find particular kinds of quantum computing like adiabatic quantum computing suitable for particular algorithms like simulated annealing and Markov models used in optimization of the machine learning. All these approaches are only in the initial stages of development, and there is a lot of scope for further development, and several applications can be created out of this. Although this presentation talks about the efficiency of the algorithms, there are many other extensions and improvements which can be made to the quantum machine learning, quantum computing, quantum information, quantum communications, etc. kind of areas. And several new theories can be obtained out of this, such as how to combine the theory of machine learning with the theory of the physics underlying the quantum computer. And how to process information on the quantum computer with minimum of error. Here there is an example shown on stage-wise development of clustering algorithms based on rule-based techniques, then parameter-based techniques such as neural networks, and then expected projection into future on some theoretical techniques such as those based on probability theory, and how that can be formulated into the quantum domain. Here is another example where several algorithms used for pattern recognition, right now running on CPU or GPU, will be running on a quantum processor, where the traditional model of processing records sequentially will translate into processing of records parallelly in the quantum domain. And several applications such as in biology or security applications or finance applications, new technologies such as self-driving car, all of these are possible applications of such algorithms. So there are several possibilities on improving the existing algorithms like cryptography algorithms using quantum computers, and also taking them into the next stage of learning algorithms versus learning algorithms, where the machine learning happens automatically on the quantum computer, such as, for example, supervised learning creates quantum classifiers, and generative modeling such as ChatGPT will create new quantum versions of a ChatGPT, where we are able to encode either the physics phenomenon of the quantum states into the ChatGPT, or we are able to encode the information which we are looking for into the subatomic particles. And this is all only 5-10 years away. If we are projecting into next 25-30 years, then even more innovation can be done using machine learning on a quantum computer. Here are some examples of such innovations, such as in molecular biology, where new drugs such as vaccines for infectious diseases like COVID can be discovered for medical application, or new materials can be created based on molecular and atomic information of the raw materials, and new space exploration applications are there, or new financial applications such as using blockchain can benefit from these developments. For example, the chemical structures and dynamics underlying them, useful in material science or computational biology, can be studied for applications such as drug discovery. And superconductivity and other states of matter, not solid, liquid, gaseous, but other states of matter, can be studied using many body quantum effects, which is a subject in quantum physics. Variational algorithms can be built to include integration of electrical engineering with computer science to form control systems and signal processing algorithms based on machine learning with minimum of error. New quantum processors can be created for quantum communication, such as in telecom sector, where repeaters, receivers, etc. can be improved using quantum computing. Also, computer science can be applied in physics to do imaging of the quantum phenomenon, to understand the subatomic particles better. At the same time, build new models in deep learning, like variational models, generative models. These are all projections of future applications, maybe 25 years down the line. However, we are only at an initial stage of this technology, and lot of work is pending. Government, society, academic institutions, companies, R&D labs, all of them have to come together to achieve some feasible, tangible sort of goals. And we are only at the stage of talking about the technology, and there's a lot of hype about it. However, we have to come to a stage of productivity around the technology, and for that, lot of work is pending. So to conclude, some of the major big picture questions which we have to address in quantum computing to make it useful for machine learning are given in these remaining slides, where we want to ask questions such as, what is the advantage offered by quantum computing compared to existing computing? Is it in terms of computational capacity, storage capability? Going beyond an algorithm, we have to think about what are the application scenarios for this technology. Similarly, will quantum computing change all the existing technologies? For example, will the way we are designing a car change according to our understanding of the quantum domain? That is unlikely, because engineering streams such as mechanical engineering will continue to decide how to design a car, because the laws of physics which apply in mechanical engineering will not change. Only when we go down to the subatomic level, the new laws of physics based on quantum physics come into play. So, from a machine learning perspective, we have to think about what kind of new algorithms, models, and theories will result for machine learning when we use a quantum computer based on subatomic particles. But if we don't want to use subatomic particles, and we want to go with the existing computing paradigms, such as the supercomputing paradigm, then there will be no change in all those paradigms. Although quantum computer may act like a supercomputer, and it may outperform existing supercomputers. One major problem because of entanglement is to isolate the quantum bits of interest for the machine learning problem from the remaining quantum bits, so that there is no error coming because of the remaining quantum bits. And one way to approach this problem in machine learning is use the black box optimization paradigm, where the building blocks of machine learning are thought of as black boxes, and generalizations are made on the black boxes by building more and more complex mathematical models, such as, for example, generative adversarial networks were invented a few years ago. Now there are diffusion models, which are foundation models for deep learning, and they are improvement on generative adversarial networks for generative modeling. And they are based on this idea of a black box optimization, where a complex nonlinear non-separable model such as a deep neural network is thought of as a black box and optimized further for generative modeling. Several such new developments, such as foundation models, mathematical models, will come about if we are able to isolate the qubits encoding the information for that black box, apart from the remaining qubits causing error in the quantum computing. However, this is an active area of research where we want to design circuits with minimum loss of energy and at the same time minimize the error in the quantum machine learning, resulting in efficient quantum algorithms. One issue in quantum mechanics is if we observe a particle, we are uncertain about it. So the quantum state before observation of a particle will be different from the quantum state after observation. So the observer has a role to play in quantum particle properties. And hence, the information which is encoded in the quantum particles is dependent on who is observing those particles. And this is called the quantum collapse phenomenon. So how to account for the observer and the observation of the particles into the information encoding and computing schemes which are designed on those particles to get the desired output from the machine learning algorithm. This is a very difficult task. And what is the nature of entanglement between quantum particles, where there is every particle is related to every other particle in the system, whether we are using that particle or not for the quantum computing. So how to keep track of the communication which is happening between the particles when we encode information into the quantum bits? This is a major challenge. Okay, so this concludes the presentation. If there are any questions, we can discuss now. Thank you.
Okay, thank you, sir. Participants, if you are having any queries, please raise your hand so that we can unmute you. Any questions from the participants?
Am I audible, please?
Yes, you're audible, sir. Okay, then I think we can conclude the session with a vote of thanks. Dr. Satyavrata Singha, sir, I request you to propose the vote of thanks.
Yeah, a very good afternoon to everyone.
Just a minute, sir. I think there is one question from one participant.
Yes.
Let me just unmute him. Okay, Dr. Prabhadev Singh, you're unmuted.
Good afternoon, sir. Good afternoon, ma'am.
Good afternoon.
Am I audible?
Yes, sir, you're audible.
So until the organizers come about, I will just stay online and I'll switch off the camera and mic.
Okay, I just wanted to ask that Google is claiming something that they have solved some problem within minutes. Okay, so can you tell something about that? What Google is claiming and whether they have developed any chip for quantum computing? Am I audible?
Yes, you're audible. Dr. Anisha, there is a question. Dr. Anish, are you able to hear? Yeah, Dr. Anil Shivukula, sir, are you there? I think he is not able to hear. Anyway, we'll pass the question to him in offline mode. Okay, I think now we can propose a vote of thanks and we can conclude the session. Satyabrata, sir, please.
Yeah, very good afternoon, everyone. On behalf of the organizing committee, I would like to extend our heartfelt gratitude to Dr. Anish Chivukala, sir, Assistant Professor, BITS Pilani, Hyderabad, for delivering a highly engaging and insightful session on quantum machine learning. Dr. Anish, your ability to demystify the complex intersection of quantum computing and machine learning was truly remarkable. The knowledge and real world perspectives you shared have opened new avenues for us to explore in the emerging field. Your session was both thoughtful and thought provoking and inspiring, leaving us eager to dive deeper into this exciting area of research. Thank you for your valuable time and contribution to this 6 days online FDP. Your efforts have significantly enriched our program and sparked a deeper curiosity in the participants. Thank you, sir, and thank you, everyone. Stay tuned for the next session.
Thank you, Dr. Singha. Next, there is one more session, two more sessions actually. Now it will be by Dr. Abhinav Kumar on integrated sensing and communications with quantum compute and AI in beyond 5G networks. So I would like to request our convener, Dr. Papia Datta ma'am, to brief about Dr. Abhinav Kumar.
Yeah, sir, 2 minutes. We are just, our resource person is about to join. So we'll just take a short break and all the participants, please be there online. As soon as he joins, we'll start the session.
Sure, ma'am.
Dear participants, very soon we are going to start the next session by Dr. Abhinav Kumar. In the meantime, I'd like to convey that after this session, there is one more session. Just 2 minutes. So after the two sessions, there will be a valedictory session. The participants must be present in all the three sessions because we are started marking the attendance. So seeing your presence in the session only, we will be marking the next 2 days of the attendance. So once the attendance is done, then around 8 o'clock, the test session will be active. Today, the AICT server is very low. So as we are going to put in the attendance, we are finding it very difficult. So it may be possible that the server is low, but don't worry. After 8:30, you can see the link in your login. I request everyone to check their login so that you don't forget your password. So if you forget your password, then in that case, you cannot join the test. Okay, so please do that and test your, you see, check your attendance. In case you don't find the link, immediately you can message us. Okay, so our resource person has arrived already. So, Dr. Abhinav Kumar, I hope you are able to share your mic and screen also. Just check it once.
Yeah, hi everyone. My apologies for the delay. I think I was trying to log in through my official ID, but there was a domain conflict. So I logged out and then joined in, so it worked. So sorry for the delay. And I'm able
It's
to,
okay,
I
no
hope I'm
problem.
audible.
Yes, sir. Just let me read your profile and then we are going to start.
Sure, sure.
For
Meanwhile,
those who
let me
are,
project the slides also. Please let me know when you can see them.
yes, it is visible, sir.
Okay, great. Please go ahead.
Okay, for those who have joined today, I just like to give a brief profile of Dr. Abhinav Kumar sir. Dr. Abhinav Kumar sir received his BTech degree in electrical engineering and MTech degree in information and communication technology and PhD in electrical engineering from IIT Delhi in 2009 and 13 and respectively. From September to November 2013, he was a research associate in IIT Delhi. From December 2013 to November 2014, he was a postdoctoral fellow at the University of Waterloo, Canada. Since November 2014, he has been with Indian Institute of Technology, Hyderabad, and currently serving as a professor. His research interests are in the different aspects of wireless communication and networking, including machine learning, IoT, and 6G communication. Welcome you, sir, in this session. Please continue.
Sure. Thank you. Thank you, Dr. Bhatia, for the kind introduction. And thank you for this opportunity to present another session as part of this program. So today we are going to discuss about integrated sensing and communications with quantum compute and AI in beyond 5G networks. For those of you who were able to join the previous session 2 days ago, we discussed about how quantum computing and AI will combine together to facilitate various use cases in the context of 6G. So I will not be reiterating that part, maybe just one slide overlapping with the previous presentation to set the context again. And then major focus for today's session will be on integrated sensing and communication as a technology in itself, and then how quantum comes into picture in various aspects of ISAC and how it can enable ISAC as a key 6G technology. So today I will not be focusing a lot on quantum compute, AI, and 6G's intersection because I already covered that. The focus will predominantly be on ISAC and where quantum, in various aspects where quantum comes into role, comes into picture to enable it further. So with that as a context, maybe let me give you an overview of today's session. So I'll start with ISAC for those of you who are not familiar with integrated sensing and communication, maybe several slides on just to set the tone on what is ISAC, different types of classification of ISAC, and then how ISAC marinates with, let's say, QML, quantum-based machine learning, and then how can we have integrated distributed sensing and quantum communication network in itself. Plus, if time permits, then I'll try to also go through a couple of works that our group has already, presented or published, which are at the intersection of network-based sensing. They're not purely ISAC, but at least they motivate towards ISAC, which is a key 6G technology. So with that as an outline, let me quickly move on to the next slide. At any point, if you have a doubt or a query, please feel free to raise hand or type a comment in the chat window, or we can also discuss at the end of the presentation based on your comfort. So this is where we ended the last presentation. If you recall, we were discussing AI, quantum, and 6G, and we looked at various use cases across the domain in terms of the location, whether it is land, air, space, water, underwater, whether it's in terms of user side, interface side, edge, network infrastructure side, core network side, and also in terms of layers, physical presentation, network application, and all. Also, there were several technologies that we discussed. One of those key technologies, like we have discussed massive MIMO last time, massive IoT, millimeter wave, terahertz, VLC, so on and so forth. So one of the key technologies there, which is going to enable 6G, is going to be ISAC, which is the focus of today's presentation. So maybe without any ado, let me quickly jump into what is ISAC. So this is a typical example of what ISAC looks like. So in future, we will have these communication networks, which are already deployed in some sense. So we have these smart gateways, which can be connecting your IoT, or which can be connected to Internet of Vehicles, or connecting to other base stations, or connecting to drones or UAVs, even aircrafts, and human beings or mobile phones. And there we can use the same signal for communication as well as for sensing, and in some cases both. So as you see here, the red signal is purely communication. There is just communication happening between the IoT connected home and the smart gateway. But at the same time, the gateway is able to do only sensing using the same signal for some target, let's say this human being, and is able to do both communication and sensing in the context of, let's say, the drones and the Internet of Vehicles, which is the focus of today's presentation, which is also termed or abbreviated as ISAC, or integrated sensing and communication. So with these different kind of scenarios possible, it is very important that we classify ISAC carefully, which is what I'm going to do in the very next slide. So if you look at sensing and communication in general, not ISAC, but if you look at sensing plus communication in general, then we can have the following classification. It's a very good classification from the perspective of only sensing, which is the top part in the slide, and integrated sensing and communication. Now within sensing, and within ISAC, we can have device-free as well as device-based. So, and I will elaborate both device-free and device-based in subsequent slides. So we can have device-free only sensing, device-based sensing. We can also have integrated sensing and communication, which is device-free and which is device-based. In each one of them, we can also have monostatic, which essentially means the transmitter and the receiver are co-located. We can have bistatic, where the transmitter and receiver are non-co-located. We can have phase array radars, or we can have MIMO radars with multiple input, multiple output systems. We can have phased MIMO radars also. Plus, we can have cooperative as well as non-cooperative localization in the context of device-based sensing. Similarly, we can have a MAC, which is multiple access channel, or broadcast channel based. Plus, we can have other devices based like relay and D2D based. I'm going to cover as many of them as possible to set the tone right, for ISAC, or at least give you a good introduction to ISAC. So I'll cover a lot of them, and then I'll try to explain where quantum machine learning comes into play and helps facilitate further, this upcoming technology of ISAC. So coming to the first part, which is just sensing. So this is old technology in some sense. This is the radar technology, right, which most of you are familiar with, which is device-free sensing. So you have an array of antennas which is sending a particular beam, and these beams are going to hit a target, and then we have a transmit array, we have a receive array. They can be co-located in the context of monostatic, and then we receive the signal, and then we try to identify the target, perform various tasks in terms of you can perform localization, you can perform classification. So various types of sensing tasks can be performed on top. Similar to this, we can also have network or wireless based sensing, where now, unlike the previous one, where we were using a dedicated device only at the sensing part, but not at the target. So please note, for device-free sensing, which is let's say typical radar, we are just, or it can be active radar, it can be passive radar also. But let's say it's an active radar as illustrated in this figure. So we have a transmit array, which that's why the name active radar, and we have a receive array, which is receiving the signal. Then correspondingly, we can also have wireless-based sensing or a network-based sensing, where if we have a device, this device can connect to the nearby networks, which can be a heterogeneous set of networks like Wi-Fi, like base station, even satellites. And then based on the received signal from these different wireless networks, we can perform sensing at the user. One simple example can be, let's say, GPS. GPS-based localization essentially is a wireless-based sensing, where there are these satellites which are already deployed in the geosynchronous orbit, and we're using them to locate or identify the location of a particular device based on multiple signals received from multiple types of satellites, or multiple number of satellites, sorry. We can also perform this through base station. A lot of you might be aware that we have base station assisted localization in the phones, where we are not only using the GPS, but it is base station assisted or cellular assisted GPS localization, where we are using the XYZ coordinates of the base station, the receive signal from the base station, not only one of them, multiple of them together at times to do triangulation, and then augment this with the GPS signal. So that can also be performed. Similar technology can be used in the context of wireless LAN. I'm going to elaborate some of these examples from our own group towards the end of the presentation if time permits. But coming back to the ISAC part, so we can have first is device free, then a network based. We can also have device based sensing. So you can have different types of these devices. We can have these anchor devices, which essentially are transmitting some sort of pilot symbols or known sequences, which are used by the agents to perform localization. And the localization can be cooperative, where let's say these agents are also collaborating, A and B are collaborating to localize or find their locations together. Or it can be non-cooperative, where each agent is just receiving signals from the anchors and then trying to figure out what is their location. As shown on the right-hand side figure, we have an agent A, which is connecting or receiving signals from anchor 1, 2, and 3 and trying to do its localization. Similarly, we have an agent B, which is performing localization in a distributed or a non-cooperative fashion using signals received from anchors 5 and 4. Now, coming to the ISAC part, and so, and if you recall the initial classification, right? So we have discussed these two, device-free, device-based, and now we are here at the ISAC part, where we are not performing just sensing, we are also communicating, right? So communication is also happening on the same channel, on the same spectrum, and ISAC itself has multiple variants. For example, the first representation here on the left-hand side is a monostatic version of ISAC, where we have a base station which is sending a communication, which is, let's say, sending a communication signal and receiving it back after it hits the target. That's why the monostatic, it's kind of like a monostatic radar, right? At the same time, it is also receiving, let's say, uplink communication signals from other users. And it is able to decode the communication signals as well as the sensing signals at the same time. So this is one representation of ISAC that is possible. We can also have a representation where we perform this in a bistatic fashion, where the base station is transmitting, and which is illustrated in the right-hand side figure, where the base station is transmitting signals. These signals are hitting various targets, let's say these K targets, then they're getting reflected, refracted, diffracted, all those permutation combinations are possible. And then the sensing signal is received at each of these user equipment at the phones. And because now the transmitter and the receiver are non-collocated. In the first example on the left side, the base station was the transmitter for the sensing signal, and it was also the receiver. On the right hand side, the base station is the transmitter of the sensing signal, but the users or the mobile phone are the receivers. And then they can perform localization or sensing using these multiple receivers, which are distributed in fashion. And then they can also use the communication channel on the uplink to communicate this, to decide what is to perform various sensing tasks like localization, classification, detection, so on and so forth. We can also have a following version of device-free ISAC. So please note these are all device-free in the sense that the targets are not devices. Unlike the previous device-based where even the agents were devices capable of communication, in device-free version of ISAC, the targets are not capable of communication. They are passive devices. They are just reflecting the signal or refracting the signal, or the signal is getting diffracted from the edges and all, right? Continuing that device-free ISAC itself, we can have the following nomenclature where we have device-free ISAC again in the context of monostatic. Now, please note, unlike the previous one, unlike the previous example where we had a sensing signal, a dedicated sensing signal coming from the base station, and a separate communication signal coming from the user equipments. Now in ISAC, we have a common signal, which is the ISAC signal. And that is why, as the name indicates, it's an integrated sensing and communication signal. So the signal itself is designed to perform both the tasks. It is designed for communication and it is designed for sensing. And that is why we can use the same signal to communicate with users on the downlink, and at the same time in a monostatic fashion sense different targets as illustrated on the left hand side figure. Equivalently, we can have a distributed version of it where we have ISAC signal being sent by the base station on the downlink. It hits the targets. The corresponding, we can, for simplicity, let's look at them as the reflections, but we can also look at the other physical phenomenon. The reflected signals are received at the users to perform sensing. At the same time, the direct ISAC signal is also received at the user. Now, please note, these ISAC signals can be combined for enhanced communication because now we have more diversity in the system. At the same time, the ISAC signals reflected from the targets can be used for sensing. So they can serve the dual purpose or dual use case of sensing and communication. But the challenge lies in designing such ISAC signals. That itself is a very interesting and hot topic of research currently in the community on what are good physical layer designs for such ISAC signals. What kind of modulation scheme should we be using? For example, OTFS is one kind of technology which has been discussed. And then after that, several other technologies have come into picture. I will not be digressing into that part because then it will become a discussion only on ISAC and we will not be able to focus much time on the quantum and the AI part of it and how they integrate. But it is important to understand that in itself, ISAC is a hot topic of research for 6G, and there's a lot of work happening from the perspective of waveform design, modulation, coding, equalization, channel estimation at the physical layer itself, and then multiple access control or multiple access technology or schemes at layer 2 and so on and so forth. So those are also very important and ongoing areas of research, very actively being pursued across the globe in the context of 6G. We can also have within ISAC device based, where, for example, let's say in uplink now, each user is sending an ISAC signal. The signal can be used to detect or to perform sensing from the users. At the same time, the signal can carry information on the uplink. So we don't have to send a separate uplink signal. And same can be done on downlink also, as you see here. Now, unlike the previous case where we were trying to sense the targets, here we can perform sensing for the user itself. For example, if you recall in the very beginning of the slides, I talked about these network-based localization or network-based sensing, where we can use, let's say, base station assisted GPS. So it is something similar here, but now we are not using regular base station signal. We are using the enhanced ISAC signal to result in better and improved or increased accuracy of sensing, which can be localization is one possible use case, but can be other use cases also. So then we can have this device-based ISAC also. Now, the device-based ISAC can be further extended, where we can have some sort of a relay or cooperative communication in the picture. As you see here, there is a relayed signal, or there is cooperative communication happening between user 1, user 2, along with the base station. So all these very interesting communication paradigms that have been explored in the context of 5G can now be re-explored in the context of ISAC, where our motivation is not just communication, but use the same signal for both sensing as well as for communication. In this context, for example, we can use it to sense the drone. What is the speed of the drone? What is the location of the drone? Is it actually a drone or not? Right? So we can even perform classification tasks. And even in our group, we have been able to successfully do that to a certain level of accuracy using millimeter wave. So that kind of work can be done on top, or in cooperative communication context, we can have these multiple users. In this illustration on the right hand side, we have 2 users. You can even have n users, and the n users are trying to cooperatively communicate with the base station, and at the same time perform sensing to enhance, let's say, localization or self-localization for each of the users available in the network. So those are some of the key classifications that are possible in the context of ISAC. And now coming to how the implementation part of it works. So this is just a simple illustration, but I think it very accurately illustrates how ISAC works. This is more from the transmitter side, but we'll have an equivalent chain, slightly more complex, but equivalent chain at the receiver, where currently, if you look at only communication modules, the communication module looks like this. You have a sequence of bits. And again, it's a simplification. We've forgone the source coding, we've forgone the channel coding and all. We are seeing just a sequence of bits from some source. We are using or transforming these bits into symbols using modulation, applying some sort of pre-coding, and then using an RF chain with various phase shifters and transferring it through a MIMO setup. Right. This is a typical communication module that we have currently available, and equivalently, we also have the following radar modules available, where we have radar signal processing with some input pulse. We apply a match filter, and we have some RF chain, and then we transmit. Right. Alternatively, now what can happen is in the context of ISAC, now we will have both these modules co-located, where we can be communicating, let's say transmitting from this communication module. This communication is, let's say, for vehicles and for these mobile phones. And there is a lot of clutter in the environment. It hits a target, and we get an echo signal. And that echo signal is received at the radar chain, the RF chain of the radar, which then passes on to a match filter, which gives it to a radar signal processing, and then we can use it for target detection and estimation. So we can even track targets now using this ISAC. Right. Now, please note, there are several use cases for this technology. We can have both active sensing, we can have passive sensing. Passive sensing is device free. Active sensing is that one with the device. So it's in some sense another nomenclature, but I thought it'll be good to expose you guys also to this kind of nomenclature. So because also this is also very commonly used in the literature. Instead of using device based and device free, we were also using passive and active in some sense. So passive means that the communication is only happening from one device. It is communicating, the signal is hitting the target of interest, and you're getting a reflection back. And then we are using that to perform sensing. And the same signal was actually being transmitted for communication, right? On the other hand, the active one is where the device, for example, in this case, the car itself is actively transmitting, and then we can perform ISAC based on the communication signal itself, and then try to figure out the location and other aspects from a sensing perspective. Please note, we can use this, although only 4 use cases are highlighted here. One is for UAV or the drone networks in terms of an aerial network. Second one is for environmental reconstruction. Third one is for smart home. Fourth one is for smart factory. But the use cases are pretty diverse. For that matter, most of the use cases that we initially looked at here, in all these contexts we can use. For example, for space communication, for aerial communication, for overwater communication, underwater communication, right? In each of these contexts, we can use ISAC, right? So it's a technology that's going to be omnipresent in some sense as you go forward towards 6G. And that is the reason why in IMT 2030, ISAC is one of the key aspects that have been included by IMT. So along with AI native communication and several other aspects like communication and computing architecture, device to device, advanced antenna technology, RIS, RAN slicing, and digital twin, ISAC is one of the key technology trends that have been, accepted across the globe, including in IMT 2030. Now, when we say ISAC in itself can have various representations. So far, we have looked at ISAC from the perspective of device-free or device-based or wireless network-based. We have also looked at ISAC from the perspective of monostatic or a bistatic radar kind of a representation. But ISAC can also be thought of as in terms of the multiple access scheme. For example, here, the left-hand side of the figure is where there are separate blocks. And this is the current state of the art. In the current state of the art, for example, in autonomous driving car or say semi-autonomous driving car, the car has a radar or a LiDAR for sensing, and it has a communication module to communicate with the network nearby, for example, for V2X communications. But now, so this is separated sensing and communication, but in the context of orthogonal ISAC, what we can say is that we are going to take the time frequency resources and we are going to have an ISAC transceiver, and we are going to split these resources into radar and communication. So this is one way in which ISAC can be performed, where let's say the pink one in the, let's presume this is pink and blue. So the pink one is for radar, the blue ones are for communication, the time frequency resources. And then we can optimize this. You can perform a lot of interesting optimizations on top. So that in itself is an active area of research on how to allocate these resources in the context of orthogonal ISAC, with different use cases, right? But then things have moved beyond orthogonal domain also, which is where people are now also looking at non-orthogonal ISAC. When we say non-orthogonal, again, it is from the perspective of resource allocation. So unlike the previous case where we were giving orthogonal time frequency resources to perform ISAC, now we might be giving overlapping time frequency resources with different power allocation. And this can be done in the spatial domain, which is what is highlighted here. So you have this certain number of antennas which are using the signal for radar, certain number of antennas which are using it as communication or private signal. And then you can perform SIC of the radar signal, successive interference cancellation of the radar signal, and then perform decoding of the private signal. This is one way to do it. Alternatively, we can also have, for example, RSMA, where in RSMA we have a common message and a private message, and then a radar signal latched on to top. And there, as you see here, the common signal is being communicated as a broadcast signal, the green one. The private signal is only for the devices which need the private signal, and the radar signal is specifically for the vehicle which you're trying to sense. And then again, similar thing happens. We perform SIC, we perform decoding and SIC of the common signal, and then so it's a stepwise decoding. We first decode after SIC of radar signal the common signal, and after that the private signal of each individual device can be decoded, right? So this is the state of the art in terms of ISAC from a multiple access perspective, both from spatial as well as rate splitting or RSMA kind of domain. Now, coming to the intersection of ISAC and quantum, so there are already works, some preliminary works which have looked at how to apply QML or quantum machine learning in the context of ISAC. Where again, please note, for example, here, this is a Wi-Fi access point, which is 60 gigahertz standard of 802.11 AD. So given this 60 gigahertz millimeter wave Wi-Fi access point, different beam SNRs are represented here, which are being transmitted by this access point. And now, if a human being is posing in between and we are receiving this signal, how can we apply, let's say, suitable machine learning to begin with to detect the pose? And there is a good amount of work which has been done in this direction without quantum also, including in our own group, which I'm going to present toward the later part of the presentation, where people have said that, okay, if I have a known received signal, can I use this known received signal from Wi-Fi or known received signal from cellular or known received signal from any other network technology to detect various things in my environment? In this particular case, pose detection has been performed. But then the challenge is a lot of times the data available is humongous. Huge amount of data available through this sensing. And the reason I'm saying this is because we have done it in sub 6 gigahertz Wi-Fi, and even in sub 6 gigahertz, for example, let us take the case of LTE advanced is a 4G technology, right? For a 4G LTE advanced, if we have 100 subcarriers and we have 10 time slots, ballpark we're looking at 100 cross 10,000, such estimates of channel, temporal and frequency based estimates. Please note, because this is happening in time frequency domain. Even if it is orthogonal, it is going to happen in time frequency domain. So we need to figure out, even for orthogonal ISAC, forget non-orthogonal for now, that problem is pretty complex to deal with. Even for orthogonal ISAC, if we are going to look at the time frequency resources, for a 4G setup, this time frequency grid is every 10 millisecond, we have roughly, let's say, 10,000 of these, 1,000 of these, 100 cross 10, right? And I'm not going to the symbol level, by the way. I'm just looking at subcarriers, subchannels and time slots, right? But each subchannel has certain number of subcarriers, and each time slot has certain number of actual OFDM symbols. So if you go to the level of subcarrier and symbol, which is what 5G does, to be precise, unlike 4G, you can do multiple device resource allocation at subcarrier and symbol level, and not necessarily you have the constraint of a resource block, then the grid size exponentially becomes larger. Almost from 1,000 size matrix, it becomes, let's say, 10,000 to a million size matrix. Now for that size matrix, we are talking about, given that size 1,000, 10,000, 1 million size metric, we want to perform, first of all, data collection, and we want to train some machine learning models. And then even the object under consideration can have different poses. In this example, they have discretized the poses. They have taken 7 poses, right? But in real life, there is a continuum of poses, right? Each human being has different height. Each human being has different form factor, size, different angle at which they will put the hand. So the pose itself has a continuum, right? So now the problem becomes exponentially larger from a computational perspective. So now we are looking at symbols, which are of the order of million plus per sample vector size, if you're looking at, and potential classifications also of not just 8, but maybe 1,000 or plus types. So this becomes a very challenging problem to solve with a traditional computing environment, and which is why a quantum machine learning based approach looks or appears to be more promising. Again, this is most of it is in research phase, so there is no actual setup available, commonly available, at least to perform this. But what people are saying is, for example, now instead of training a regular machine learning model, can we train a quantum machine learning model which will be running on a quantum processor, where we'll be using the following kind of setup, where we have the beam SNRs, we have an input layer which performs transforms it into qubits. These qubits get passed on to layers like an embedding layer, an entangler layer, a measurement layer, and then the output gives us some sort of let's say ranking, to simplify it, in terms of the potential poses that are available, right? Now this is very interesting because here, because we are able to represent the information in the machine learning model itself in qubits, we can actually run this on a quantum processor, and then we can parallelize it across potential set of states. So larger the number of states, faster this is going to be compared to your traditional digital computing setup. Similarly, larger the number of input vector or the features the input vector has, larger gains potentially would be observed in the context of a QML model compared to a traditional ML model. And which is why people have also proposed not only a very higher level machine learning model in terms of the block diagram, people have gone into the details of what kind of sub-blocks might be available. It can be based on angle embedding, it can be based on IQP, it can be based on entanglement in terms of strong entangle, basic entangle. It can have tensor tree net, or it can have a random connections inside, right? So that kind of work is also happening currently. So there's a lot of, I'm not going into the details of QML part, but there is a lot of active work happening in the context of QML, where people are saying once we are able to enable quantum compute, we should be able to accelerate machine learning using QML, right? And which is where in the context of ISAC, QML is really attractive, because current compute facilities are turning out to be rather limiting factor in the context of ISAC and ML. So not only from a QML perspective, we can actually use, so this is another example, an alternative example where we are saying, let's say we have these wired connections, right, between different entities, or wireless connections between different entities, which is a quantum communication network for now. Can we use this quantum communication network to perform sensing also? So this is slightly different from the ISAC, traditional ISAC that we have been discussing so far. This is more from integrated distributed sensing and quantum communication. So we are using an existing quantum communication network to perform sensing. So we can have different representations, continuous wave representations for information within this quantum communication network. And then this is just a representation of the same thing. So you can have different child nodes, you can have a central node, and this we might be sending these qubits, across this network. Now, if there's a vibration in the network, this vibration can be an actual vibration, for example, which is what this particular archive paper looks at. It can be an earthquake, for example. Then this vibration will affect the qubits in some sense. Now, in this example, let's say there is some sort of phase which is getting captured due to the vibration. Now we can zoom in actually to this and say, okay, we have these different optical fibers, we have a splitter, there is an earthquake happening here. Then at the central node, we can use this information, we can sense this environmental aspect using the existing quantum communication network. Or to illustrate this, we have this earthquake happening here with respect to the original representation. Then based on the different changes in the received signal across the nodes, child nodes, we can try to detect various physical aspects of this earthquake, or sensing various aspects of this earthquake. So this was in terms of the QML, and in terms of the how a quantum communication network can be used in itself for sensing. For rest part of the my slide, what I'm going to do is I'm going to present how traditionally people have used, in particular in our own group, have used different communication networks for sensing. Just to motivate, that this ISAC term that we have been discussing for 6C is actually a very crucial technology, because even without fine-tuning the waveform, even without fine-tuning the network for sensing, if we use just off-the-shelf existing networks, that itself results in significantly accurate and highly precise sensing in the current infrastructure also. For example, currently we have different types of localization, detection, and classification technologies available. The traditional localization can be in terms of angle of arrival, it can be in terms of trilateration, triangulation, proximity-based, scene-based, where we can have different communication technologies, right? We can have a 2G GSM-based technology, or we can have a UMTS 3G, or we can have LTE 4G, or LTE advanced 4G, I should be saying. And now we even have 5G deployed in the market. So we can even use these existing technologies for both sensing and communication, right? Which is I'm going to highlight through some of the works that have been done in our group. For example, in this particular work, we used millimeter wave radars, and we were able to apply machine learning on top to perform sensing to reasonable level of accuracy. In this particular work, we had a 3 transmitter, 4 receiver setup for millimeter wave, and we were using a particular type of drone and trying to see if we can, localize this, estimate its angle of and height, for this aerial vehicles using this millimeter wave radar setup. And to do this, we performed initially data collection. So we took the drone, we set the drone in various locations with respect to the transmitter, and we collected data. For the data collection part, we had the following setup. We had this 77 to 81 gigahertz millimeter wave radar setup. For this particular radar setup, we collected the following chirp information. We collected around 128 chirps, and we had around 200 frames, right? So, and then for every antenna, we collected this. So for every antenna, we had a 200 cross 128, right? And then we applied standard range FFT on top of this data to perform angle estimation, using the 4 received antenna signals. This is just a summary of the hardware setup that we used. And in this particular work, please note, we are just trying to sense the angles, right? So this is, for example, different horizontal distances in terms of meters. 1.5, 2.5, 3.5 up till 8.5, different heights or vertical distances. Again, let's say, from 0.51 till 5.5. And we were able to get a root mean square error of within 0.5 meters. Similarly, for vertical distances and almost 0.2 meters for horizontal distances, right? Which is a reasonably good accuracy to get for a radar system, which is not very commercial grade radar. It's a very low cost of the shelf board. Not only this, we said, okay, motivated by these results, we wanted to see if we can perform better in terms of both object classification and not just localization. So for the same setup, for the same radar setup, so everything else remains the same. As you see here, millimeter radar, it has a frame structure, which is the same frame structure. We perform range FFT, which is a 1D FFT, and we look at the amplitude profile per chirp. And then we try to do feature extraction on top. We try to extract features like the peak height, if there are peaks available, what is the area under the curve for the peak, what is the width of the peak, what is the distance of the peak, and what is the standard deviation of the peak. Right? So with these kind of features, we applied some very off-the-shelf machine learning algorithms like logistic regression, IA-based algorithm and all, and then try to perform object classification. Please note, for this radar, it is a FMCW radar, so the frequency, transmitted frequency, as shown with the red curve, it keeps on increasing. And then it hits a endpoint, then after each chirp, it drops, and then again starts. Right? And then after a certain amount of delay, TD, we have the received signal, which is going to be similar to the transmitted signal, right? It follows it with a delay. Now, the interesting part is for this particular setup, we were able to get very distinct profiles based on the type of object. So these are the results for the 1D range FFT. So the x-axis is the distance, the y-axis is the power in some sense, or the relative power in some sense. Whenever it's a human being, a pedestrian, this is the kind of peak we were getting. Similarly, for a car, we were getting one major lobe and several side lobes because the car has multiple points of reflection and it's a wide object. Whereas for a drone, because the area under the curve is low, the object is small, so the overall reflection coming from the drone is small compared to a human being or a car, as well as the standard deviation and all is also small. So if you look at the standard deviation, 0.34 increases for car, 0.42 decreases significantly for the drone, because the drone is a very small size object relative to the car and the human being. So motivated by this, we applied the logistic regression and IA-based algorithm, and we were able to get reasonably good results. In a lot of cases, we were able to get almost 100% accuracy in detecting certain types of objects. This was a very preliminary work that we did, and then we said, okay, can we do better? So one thing was in the first work that I presented, we looked at the height and the distance, or height and the angle in some sense. So we wanted to improve that. To improve that, we performed or we presented a novel angle of arrival estimation based algorithm, where we were able to enhance it. In interest of time, I'm not going to go into the detail of the algorithm, but we also generalized it to larger number of people in the radar system. So if you see here, the first work we looked at was single object drone. Second work was multi types of objects, object classification. In the third work, now we are saying multi objects. With multiple objects in the coverage of the same radar, can we detect them? Can we localize them, or at least tell their angles? So here we have multiple objects, and this is how the legend should be read. This is person 1, 2, 3, 4, 5 based on the color code, and we have different locations available, right? A, B, C, D, and all. So and with different angles, we generated this. So we created several cases, up to different 15 cases. And for this setup also, as you see here on the right hand side, this is the 3D plot. Unlike a 1D plot for a single object, now we have a 3D plot because we are covering all the angles. And for each angle, we are not averaging out the result. Now we are trying to take across the angles, individually. And so that is why we have a range and angle profile. For such a range angle representation, we have 3 peaks now, each peak corresponding to a different human being. The peak size is definitely a function of the distance, it is also a function of the object itself. So if I'm going to replace a human being out of these three with a drone, the peak size and the width all is going to go down. If I'm going to replace any one of them with a car, as shown in the previous work, accordingly the peak is going to vary. So in theory, we can perform multi-object classification and localization at the same time by suitably representing them in the range angle representation, which is also very similar to the delay Doppler profile that we are talking about, or people are talking about in the context of ISAC, where in ISAC you have this delay Doppler representation, let's say in OTFS, where in the delay Doppler representation, each object which is predominantly reflecting a signal turns out to be a peak in itself, right? With its own range and delay Doppler or range Doppler kind of a profile. Because please note, range and delay can be interchangeably used because we are using the same RF signal. So whether it is range or it is the amount of time taken by the RF signal to traverse that range, the two can be equivalently represented, right? So that is why there is an equivalence between this representation of range angle and the delay Doppler that we talk about in the context of ISAC and OTFS. Now coming to the next part. So this is the algorithm part. I'm going to skip the algorithm part in interest of time because I have a couple of other interesting results to present. But as you see here, if you look at the heat map, there is this heat map based on the number of objects available at different angles. So we collected this data for several angles and several range profiles. And as you see here, the estimated angle, the RMS value was within 5 degrees, right? Which is a reasonable, RMSE value. We further applied polynomial regression model on top, and we were able to reduce the RMSE to 2.5 degrees. So this was the work done on millimeter wave radar systems, which are actually used for sensing only. So if you recall the very beginning of my presentation, I talked about ISAC, and I talked about two types of localization or sensing technologies. One is sensing only, the other one is ISAC. Within sensing only, we looked at device free, device based. So this is essentially the first part is device free sensing, where we are using off-the-shelf radars. The device is not smart, it is not communicating anything. The human being or the car or the drone is not communicating at all. We are just sensing them by using the radar system. Now for the second part, which is vehicle classification and localization using LTE, this is similar, but this is using the communication network. So if you recall the second part of ISAC, there in ISAC itself, or within the first one also, there was a slide on network-based sensing. So this is an example of network-based sensing, where for this particular work, we wanted to identify objects which are cars. We not only wanted to identify the object in some sense, we wanted to see if a particular parking slot has a car present in it or not. So for this particular work, because we wanted to test the presence or absence of a car in a particular block, we used off-the-shelf LTE communication signal from third party. We just latched on to its pilot symbols. And then we used user equipment. Maybe the next slide will be better to elaborate this. So what we did was, for the training path, we just captured the LTE downlink signal using a USRP. And then we extracted out the channel information. We use this channel information along with our known labels of whether a car is present in a particular parking slot or not. This was performed within our campus. And then we trained a CNN model on top. And then basis this, we were able to generate a database for this particular parking lot, which can give you the vehicle count, which can give you the location of the vehicles. And then we performed classification for occupancy status detection, and we were able to calculate the accuracy. Now, given this training path, for testing path, we just take, again, using a LTE, open LTE framework, we extract out the channel information for the testing path, we feed it to the trained model, the CNN-based model, and then the model itself tells us whether a particular parking slot is empty or not, right? And for those of you who are familiar with CNNs, this is a standard CNN layer. We have 3 convolution layers. You have a fully connected layer and an output layer. This is the input layer. And now, please note, the important part is, and that's one of the reasons why we didn't use off-the-shelf supervised learning algorithms, because if you look at the input signals here for the 4 scenarios, it is very difficult to tell from the input signal itself that whether it is 1 car, 2 car, or 3 cars, right? Also, because this is the labeling part was done by us. So we could apply a CNN based architecture from a machine learning perspective. And this is a simplification of the use cases that we considered, but because of the space and time constraint, I'm presenting this one. So let's say you have 4 cases. In first case, in parking lot, in parking spot B and D, there are cars. In second case, in A, B, C, there are cars. In third case, in only B, there is a car. And in fourth case, there are no cars, right? And similarly, we can have various permutation combinations of this, right? So we were able to, and this is the corresponding equivalent representation. So case 1, 2, 3, 4, these are the signals, right? As you see here, these are very close to each other. So it's very difficult to resolve them using traditional ML approaches. And that's why we have used CNN-based approach. And with that, we were able to get around 95% plus accuracy, comparing it with the state of the art at that point of time, which was PCA and SVM based, which were giving only 50% accuracy. Also, the existing works are mostly for single car, whereas we were looking at multiple cars or multiple parking spots, right? And we were able to get, so this is in terms of number of cars and the parking spots, location of the parking spots. So 95% accuracy in terms of number of cars, 90% accuracy in terms of which spots are empty, which spots are occupied, the localization of the cars. So this was using a LTE based network. We were also able to redo this in the context of Wi-Fi. So again, Wi-Fi, the assumption is this Wi-Fi, just like LTE in the previous example, is already being used for communication. So communication is already happening on this Wi-Fi network. We are not touching the communication part. We are using the existing Wi-Fi deployed in a particular setup and latching onto it passively in some sense and trying to localize. So for this particular work, we wanted to perform multi-building 3D indoor Wi-Fi localization, again using CNN-based approach. Based on our past experience, we knew that for channel state information, a CNN-based approach turns out to be better than regular ML-based approaches. And here we can perform human detection, human occupancy counting, human movement detection, human tracking, which is similar to what we have seen for the QML-based work. If you recall, for QML-based work, they were doing gesture recognition or pose recognition, right? How a person is standing, hands straight, hands up, so on and so forth. So all that can be performed using traditional ML-based approaches also. We don't necessarily have to go for QML, but then the motivation is the moment you start using QML, the kind of accuracies you're going to get is going to be exponentially higher, or not exponentially, maybe is not the right term, but significantly higher than the regular ML-based approaches. For this particular work, we were looking at sub-6 gigahertz Wi-Fi. The data set is publicly available actually for this third-party data set is there. Just to position the work, please note this was not the first work which performed multi-output or 3D localization. So there were several works available at that point of time. Several of them had also used CNNs. Some of them had high accuracy, some of them had medium accuracy. Some of them were looking at only 2D. Few works were looking at 3D at that point of time. Within 3D, few works dataset was publicly available. For most of them, dataset was not available. The output of some of them was multiple outputs in terms of, for example, let's say, are we looking at which building, which floor, which location in that floor? That's the kind of localization we want to perform using pre-deployed Wi-Fi network, right? So we use the fingerprint image-based approach for this. And to perform this, we use this UGI indoor location database. It's a third-party database from Universitat Jameh 1, which has 4 or more floors, 3 buildings. They use 20 users with 25 different type of mobile phones and connected almost 20,000 samples for training or calibration and around 1,000 samples plus for validation and testing. Each sample here is effectively a row in the table that I'm presenting, where each row corresponds to 520 access points receive signal strength. So first 520 elements are just receive signal strength from each of those access points. And then we have also the label that which building it is, building number 0, 1, 2. So 3 buildings, right? So 0, 1, 2. Which floor? So 0, 1, 2, 3, 4. And which space ID within that floor. So that's the kind of labeling already available in the dataset. And what we did was we took this dataset, we applied image construction, and for training part, we did a fingerprint classification, a fingerprint image construction, and a CNN training. And what do we mean by this? So we take the vector, the 520 actually 523 size vector, 520 plus 3, 523 size vector. And first of all, we pruned it. So why did we prune it? Because we realized out of those 523, almost close to 36 of them, 26 of them are always 0. So we never receive any RSSI value from 36 access points at any point of time. So what's the point of considering them? So we just removed them. We reduced the vector size. We also took this vector and converted it into a grayscale. And why a grayscale? Because once you convert it into a grayscale image, the image-based machine learning algorithms are more, better available algorithms are there. Pre-trained algorithms are also available now in some sense. So hopefully the accuracy is going to be better. So we took a grayscale 22 cross 22, then we fed it to a CNN of the following architecture, and then we perform multi-level classification. Each classifier, one is for building. The building classifier gives a building ID. The floor classifier gives a floor ID. The space classifier gives the space ID. So which building, within that building, which floor, within that floor, which space, right? And the advantage of representing this in this image format is that you can do a lot of optimization in how you construct the image also, right? But in the interest of time, I'm going to continue this and just present the results. So for this particular work, we were able to get with the proposed CNN around 98% accuracy for training data and 97% accuracy for the testing data. And compared to other traditional machine learning algorithms, this was significantly higher, especially in terms of the test data. This particular work was also awarded as Best Paper Runner-Up Award in National Conference on Communications in 2022. So I wanted to just highlight these works to showcase to you that ISAC is possible even with the current deployed networks, but the kind of accuracies we are going to get is going to be not so high, especially in the context of newer environments. Please note, for example, for this particular work, for all locations in all those buildings at all floors, the data was available, right? But this requires mapping to be done from the network perspective, which in itself is a cost. Now, this can be done for 4 buildings. This can be done for 5 buildings. But if you're looking at a city level, if you're looking at, a metropolitan area level, then this becomes a humongous exercise, which is very difficult to perform. So to collect such labeled data sets for very large size areas is extremely difficult. Then alternatively, the solutions are, can we create some pre-trained model on certain types of locations and then reuse them? So let's say housing societies. So I am from Hyderabad, so I'm going to give an example from Hyderabad. Let's say in Hyderabad, we have a lot of these housing societies which have buildings which are like 10 floors, 20 floors, 30 floors. Now even 40 floor plus buildings are coming up, right, across, let's say, the Gachibowli area. So if we collect such data of Wi-Fi network for one set of such society with 10 buildings, 20 buildings, can we create a trained model and then retrain it with minimal effort for another society? I think that's the kind of work we should be looking at, which will have a lot of value, because training, retraining might be requiring less number of samples to be collected in the new location, right? But then the accuracy of such setup. So this is effectively like transfer learning or domain generalization, domain adaptation kind of a setup, based on whether you view this in terms of the class itself being new or in terms of the distribution being different and also and so forth. But the underlying assumption is, so for our understanding, to keep it simple, let's call it transfer learning. So it is all like transfer learning kind of an approach where we train a particular model based on a training data set and transfer this learning to a new environment or a slightly new environment and use it there with minimal training. But this kind of setups currently are not giving that kind of performance. So the ones, for example, here we were able to get 98% accuracy, right? So with transfer learning currently are not getting that kind of results. And that is where I foresee a lot of quantum-based machine learning or quantum computing-based efforts coming into picture, because hopefully if we can collect initially itself the data, because instead of having this kind of a representation, if you again go back to the beginning of my slide today, where we looked at a QML-based model, if we can collect the data from that QML-based model itself, significant amount of data for certain locations, then and because it's not binary in nature, right? It is in some sense theoretically it's continuous in nature, right? So so then it can be better tuned to newer environments, hopefully. So quantum transfer learning kind of an approach is something that I foresee gaining a lot of traction as we go forward. It's going to be a very hot topic of research, where we should hopefully be able to apply with minimal retraining pre-trained quantum machine learning models to newer environments. And that is what I foresee, maybe not in the context of 6G again, as I mentioned in my previous talk also, most likely after 6G, beyond 6G, but that is where I foresee this, a lot of growth happening in this, or a lot of research happening in this domain at intersection of ISAC and QML or quantum machine learning for 6G and beyond. So that is by and large what I wanted to cover as part of today's session. Again, maybe I will skip this. I'll just project my email address. If anybody you know is interested to pursue a master's or a PhD program at IIT Hyderabad, we have a 2-year master's, a 3 years MTech RA, and a regular PhD program across 4 streams. We have communication, signal processing, and learning that I belong to. We have pilot production power systems, microcontrollers, and VLSI, and control systems, or systems and control as we popularly call it. Please feel free to reach out to me. I'll be happy to assist you or guide you or reconnect you with somebody who can help you better, to understand the admission process. So with that, I would like to conclude my slides for today, and I'll be happy to answer any comments or query. Yes.
Thank you, sir. Participants, if anyone has any query, please raise your hands. So that we can unmute you. Okay, no queries. Then in that case, we will move to the forward for the vote of thanks. I request Dr. Satyabrata Singha, sir, to propose the vote of thanks.
Bhavya, there is
Yeah,
one
I
query.
think Praveen Kumar is having a question. So I'm just unmuting him. Yes, Mr. K. Praveen Kumar, you're unmuted.
Good afternoon, sir. Sir,
Hi, good afternoon.
Could you, so a little bit elaborate on that parking problem, sir, actually. So, you have gone through, so very speed, actually, I could not able to capture it clearly. What is exact problem? How here we are solving that parking problem, actually?
Okay, sure. So what we wanted to achieve was, for an outdoor parking environment, for an open parking setup, we wanted to sense passively which parking slot is available, which parking slot is occupied.
Sir.
And we wanted to do this using pre-deployed LTE network in our campus. So there's already this third-party commercial base station from an operator, which is continuously transmitting or broadcasting, let's say, pilot symbols, right? So we wanted to use these pilot symbols free of cost through a USRP. So we used so there is a library called SRS. More details of the library are available in the paper itself. They are using that library and using off-the-shelf USRP, which is I think we used an NI hardware for this. We were able to latch on to this base station's pilot symbols, like listen to them and extract out CSI.
So the point is that one, so when the signal is so bounces back, so we come to know that one it is occupied.
Yes.
Such a concept, no, sir, right?
Yes, that is correct. But then we are not looking at one slot, we are looking at multiple slots together.
Okay.
And because we are looking at multiple slots together, we wanted to use machine learning instead of using traditional rule-based approach, because more the number of slots, more the number of permutation combinations, more difficult it gets to design a rule. So if it is only one slot,
in the sense, various locations,
various slots, so each of this is a slot. So this is first car is in one slot, second car is in one slot, third car is in one slot, fourth slot is empty, fifth slot is empty, so on and so forth.
Yes, sir.
So with larger number of slots, we wanted to identify which slots are occupied, which slots are not occupied. And to do that, we use this LTE signal, applied machine learning on top, and then performed classification.
Right, sir. Okay, so we got the training data. So what is the trend is there actually? So we trained the model.
Yes.
And okay, so when the new information is given to it, it is giving me that, okay, so whether it is
Yes, it
empty
is
or
telling
not. Yeah.
which one is empty. Out of the
Which one
many
is
slots, which one are empty, which one are not.
yeah, yes or no concept. Okay, so the binary classification
Yes,
for
yes,
each and every parking slot area.
yes, that is correct. And we were able to do this part up to 90% accuracy.
So it's going to be a multi-class or binary class only. Yeah.
No, so in this case, you can look at it as a vector
Yeah,
classifier.
vectors. Yes, yeah, vector
Yes,
classifier. Because okay, so where vector is okay, so zero it is empty, and if it is
yes,
one, okay, so it is filled up.
yes,
So
yes.
okay, right, sir. Thank you, sir.
Sure, sure.
Bye.
Thank you. Please have a look. Just have a look. This is available on IEEE website. Have a look at this work by Amla, Soni, Prabhat, myself, and Professor Zafar, who is a colleague of mine. Dr. Amla recently finished her PhD, I think 3 months ago. Do have a look at the work if you're interested, and if you need some assistance, I can connect you, and we would be happy to help.
Sure, sir. I'm working in Guntur Vignan University, so definitely it's possible. I'll definitely contact you, sir.
Sure,
So,
sure. Please do, please do. My email is at the very
yeah, yeah,
end,
I have
but
taken, sir. Yeah, yeah. I have
okay,
noted
sure,
down. Thank you.
sure,
Thank you, sir.
sure.
Okay, thank you. Any other participants who wants to ask any queries, please raise your hand. Because it's the last session of Dr. Abhinav Kumar. So if you want to ask anything, you can connect him with him with the mail ID also provided. Okay, thank you then. Moving forward, we'll request Dr. Satyabrata Singha, sir, to propose the vote of thanks.
A very good evening, everyone. On behalf of the organizing committee of this FDP, it is my privilege to extend our heartfelt thanks to Dr. Abhinav Kumar sir, professor at IIT Hyderabad again, for his second session of this FDP, for his enlightening session on integrated sensing and communication with quantum computing and AI in beyond 5G networks. Sir, your session was a deep delve into the future of communication networks, where you skillfully highlighted the role of quantum computing and AI in transforming sensing and communication technologies. Your insights into the integration of these advanced technologies was very great, and thank you for sharing your recent development and work based on this vehicle localization and using LTE. This has not only expanded our understanding but also inspired us to explore innovative applications in this domain. Thank you, sir, for sharing your expertise and for being an integral part of this FTP in two of the sessions. Your contribution was been truly valuable, and we deeply appreciate your efforts in enriching our learning experience. To all the participants, thank you for being active for this tireful three sessions actually today, and we will be moving forward to the last session of the day. Thank you, everyone.
Sure. Thank you. Thank you, Professor Satyavata. Thank you, Professor Bhatia, for inviting me. And thank you, everyone, for joining the session. Have a good day.
Thank you,
Bye.
sir. Thank you. Thank you.
Thank you.
Okay, dear participants, our next session is going to start at 5 o'clock. So we have a little bit of time. You can take a short break. Be there in the session because if we leave, we may not be able to join. There is some network issue. So just be there. Within next 5 to 10 minutes, we're going to start the next session. Thank you. Sitaram sir, can you please unmute and check the mic and share the screen?
Good evening, Dr. Bapia. Are you able to hear me?
Sir, yes, you are audible, sir. Fine. Okay, then we'll start the session. Shubhadev sir, you can start.
Yes, ma'am. Thank you. Good evening, respected speaker, all my participants. It's a long day, and we have come to the final session of this FDP on the sixth day of AI and quantum computing, the future of intelligent systems. So now let's welcome Mr. Sitaram Todepalli, Vice President, ML Engineering, with the topic AI operation in the real world. But before that, I would like to ask and request our convener, Dr. Papia Datta ma'am, to just brief about his profile. Thank you.
Welcome, Mr. Sitaram Tadipalli sir, once again. Mr. Sitaram is a seasoned technology leader with over 18 years of experience in innovation, individualization, solution designing, and strategic development. He currently serves as the Vice President of Machine Learning Engineering at DBS Bank, where he leads the machine learning platform team. Mr. Sitaram is responsible for developing and implementing a comprehensive suite of products that cater to every aspect of machine learning lifecycle management. These products range from AI protocol and governance, model training and experimentation, batch and rest deployment tooling, feature transformation tooling, monitoring, and explainability. His area of focus is the field of machine learning, MLOps, enterprise AI model governance, responsible AI framework, and enterprise grade feature store solution. He is actively involved in the industry, serving as a senior member of the IEEE and life member of the Cloud Computing Innovation Council of India. He also acts as chair for Technology, Engineering and Management Society IEEE Hyderabad section. Mr. Sitaram holds a bachelor's degree in Electrical and Electronics Engineering from Jawaharlal Nehru Technological University, Hyderabad, and a master's degree in Data Analytics from BITS, Pilani, India. He is currently pursuing his PG program from IIIT Hyderabad in Privacy, Fairness and Ethics in AI. Thank you, sir, once again in this session. It's over to you now.
Thank you, ma'am. Let me quickly share my screen. I hope this screen is visible. Can you confirm if the screen is visible?
Yes, sir, it is visible.
Okay, wonderful. So thank you everyone for joining. I'm sure it might be a long day for you, and this is the last session. I hope I'll give much more uh, insights on how we do regular AI ML ops, specifically in the industry. So my expertise is predominantly in industry, so I would like to give my perspective. You might have certainly heard of different perspectives from other great speakers previously, but uh, this session would be more from an industry oriented. So if you have any questions or anything, feel free. You can put them in the chat window or maybe in the question answer session, and then I'll be able to answer them in the end. Okay, so with that said, let me quickly start. So this slide, I think Dr. Bapia has already spoke about a little bit about me. Close to 19 years of experience in IT, and currently serving as VP for DBS Bank. So because my background is in banking, I would like to take this example of a bank called as ABC Bank, and I want to take you guys like say 20 years in back in the time machine. So imagine like if you are in the year 2000 or so, and there is this bank called as ABC Bank. The regular operations of these ABC Bank goes like this, right? So imagine if in the year 2000 we have to physically go to the bank. I want to withdraw money from the bank, or I want to deposit a money. I want to say open a housing loan account, or maybe do an FD. All these operations typically used to happen in a physical mode, where the people have to go to the bank and do the transaction. So if you see like 20 years back, the regular transactions happen like this. So there will be a teller or maybe a cashier or a clerk where we do the transaction. It can be a withdrawal, it can be a deposit, it can be opening up a new account, opening, updating a nomination, or creating a demand draft, requesting for a checkbook. So all these regular, what we call as a transactions, all these transactions typically used to go and sit in something we call as operational data stores. Now, ODS is the short form of it. They're called as operational data stores. These operational data stores typically they are the RDBMSs of the world. The RDBMSs will be Oracle, MySQL, or PostgreSQL, similar kind of databases which are predominantly in the relational like life cycle, and they are typically created for storing relational data in a structured format, data which is having rows and columns as a template. So most of the bank's transactions, it can be withdrawals, it can be deposits, it can be retrieval of some information, and all that stuff used to go and sit into this RDBMS. Now, I've already taken you back 20 years, 25 years back, and then we are talking about the year 2000 and how the transactions used to happen. So back in those days, if somebody, a senior official from the bank, wanted to do data analysis, AI, machine learning, or similar kind of data analysis, the questions used to be like, which banks are making more profits? The banks which are having higher increase in the customer base, the banks which are making more loan acquisition or interest gathering, banks which are having the highest average customer balance, right? So all these information, imagine the CEO of the bank is trying to get the people. There used to people, we call it as data analysts. So these data analysts used to do these jobs. So the data analysts typically what they used to do is to run SQL queries on these RDBMS tables. Typically, SQL queries will be select queries where we are trying to gather information from these RDB messes and then trying to create some kind of outcome. For example, I wanted to know how much is the average balance, average monthly balance for customers across the bank. And then I want to create a report for all the banks within the territory of, for example, say Telangana or Maharashtra or part of the country. For example, I want to create such kind of reports for different geographies, different territories, and so on. Typically, these data analysts used to run these SQL queries, and those SQL queries used to be run on these ODSS databases. ODSS, typically we call it as operational data stores. So we used to run these SQL queries on these ODSS. Now, so as the number of transactions have grown, what happened is many transactions were happening in the actual real world. For example, there are lot many withdrawals happening, lot many deposits happening. There were more FDs getting created and all that stuff. And at the same time, data analysts used to run these SQL queries on the same RDBMS databases. So if you see that there generally used to be this kind of a deadlock kind of a situation where the systems used to slow down. There are a lot of bombardment of the queries, and because of this bombardment of the queries, the actual business used to slow down, right? The actual transactions. For example, I do a deposit, I do a withdrawal, I do a fixed deposit. So all these actual transactions used to have problems because there are long running SQL queries, which are analytical queries, which used to run during the day. Now, to overcome this problem, what people started doing is, okay, let us not run the SQL queries in the morning. We will run the SQL queries in the night. So that was one of the prominent solution. People said that, okay, if the banks operate from say 9 o'clock to 3 o'clock or 9 o'clock to 4 o'clock, which is what we term to call it as business hours. So these are the business hours. So business hours are starting from 9 to say 4 o'clock. Then we will run the jobs in the night, and that's where a lot of analytical work used to be pushed into the night jobs. So in industry, we call it as nightly job batch processing, where all these analytical jobs used to run in the night, where the typical business used to happen in the morning. If you see like 20-25 years back, that used to be a regular trend, where mornings used to be open for business, and the night there used to be more of a back office kind of a jobs used to run. And these jobs purpose is to do these analytical queries and then create reports, so that next day morning, if the executive comes, by the next day morning, these all jobs will create required reports in whatever format and will be available for the senior executives to take some decisions, or do some kind of decision making. Now, I'm talking about an example of a bank, but we can replace this bank with any other industry. It can be manufacturing industry, it can be a retail industry, it can be anything like media industry or travel, hospitality. So all the industries back in those days used to follow this kind of a structure, where morning used to be a regular business hours, 9 to 5. Then in the evening, late in the night, say 8 o'clock, 9 o'clock, 10 o'clock, there used to be jobs which used to run in midnight also. And the purpose of these jobs is to create these kind of analytical outputs. Analytical outputs are created, there are reports created, there are dashboards created. All these are created so that the senior executives can look at them, view them, and take some meaningful decisions. Now, this used to work for many years. I think 4 or 5 years it worked really well. But what happened is, there are two problems which caused a lot of issues. The first one is the internet expansion, and the second one is the geographical expansion. If you remember, 20-25 years back, there was a lot of advancement in the internet. And because of the advancements in the internet, what happened is the businesses no longer used to run in a 9 to 5 fashion. For example, the businesses went on to web, the businesses went on to mobile, so that anybody was able to do transactions, whether it is day or night, it was not a problem because they used to go www.abcbank.com and then they used to log into the system and they can do transactions. At the same time, there were mobile apps which were created somewhere around 2006 to 2010, that time frame where people have adopted. They don't need to go to a website. Also, they can have these apps available, and because of the apps, we can do transactions 24 cross 7. So the businesses have pivoted into a system where they are no longer confined to a physical 9 to 5 boundaries, but they have expanded the boundaries 24 by 7 because of either the web-based portals or maybe the mobile-based devices. That was the first problem. The second problem was the companies also expanded beyond the geographical boundaries. For example, the companies in US, they had these US based US based headquarters, but they are no longer in US, but they also expanded to US, Australia, they expanded to UK, they were in Dubai, they were in India. So the companies also expanded their bases across the continents. And because of this geographical expansion also, there was no such what we call as a lean period. Lean period in sense, okay, this is the time where I can run my job so that it is not impacting any other actual users, right? So there was no such lean period in which data analysts, data scientists can run their jobs and say that, I will create reports, I'll create queries, I'll create whatever required things. So because of these two issues, there was a strong push to disconnect the actual queries which are being run on ODSs, not to run on ODSs, but to create a separate kind of an environment where these jobs can run. And that's where the system of data warehousing came into picture. I'm sure you might be familiar about data warehousing. A lot of theoretical thing is there, but the way data warehouses are created were predominantly for these reasons, where we are creating this kind of an decoupling between your actual stores and the warehousing stores. Actual stores of the data are storing the regular transactions, whereas the warehousing stores used to create a copy of the data. Sometimes the data could be a pure replica of the actual store data, or sometimes they used to do something called as transformations. People used to call this as an ETL. ETL is like extract, transform, and load. So you extract the data from your ODSs, do some transformation. Transformations could be merging couple of columns, dropping some of the columns, joining couple of tables, creating more abstracted, aggregated informations. All that stuff used to be done where you keep the ODSs and the data warehousing separate. So when you decouple this, the greater advantage is you do not have this problem of internet expansion, geographical expansion. You are not bounded with your 9 to 5 kind of things. All the analytical queries used to run on warehouses or the data warehouses. So data warehouses typically were nothing but your exact similar kind of a copy, similar kind of nature of your ODSs. The great advantage the data warehouse provided is the first one is the decoupling, and the second one is the data warehouses also had the ability to store historical data. So, for example, the transactions which happened today, the transactions which happened last year, the year before, anything which was happening to a particular table, structure, business, and so on, we were also having the ability to store historical data. Now, when we are able to store historical data, we are able to do comparative analysis. We are able to do something called as change data analysis and so on, so that we can understand that what are the things changed over time. So you could also provide this kind of a notion in which you can do in a time-based manner, like how the businesses changed over time, how the customer adoption changed over time, how the money movement changed over time, and so on. So you will be able to provide that kind of angle also.
Sir,
So
your slide is not moving or it is not in a slideshow also. Can you please check once?
It is not moving because I am not moving. Is it?
Okay, it's not in a slideshow also. Maybe it's just one of the
It is.
slide is showing this together. Just to check once.
It is not in a slideshow.
Oh,
If I click next, there is data lakes popping up now. Is it? No.
no, it's not coming actually. Next slide is not moving.
There
Now
is
it is
only.
moving. Yeah, it's okay, but you can put in the slideshow. It will appear bigger. Fine.
Oh.
Yeah, it's
I,
okay, fine.
it is moving now.
Yeah, it's moving now, sir. Yeah.
Previously, you were only seeing one picture.
Yes, yes.
Oh my God. Sorry.
Okay.
I am really sorry. Okay, so I'm here. Okay. Uh, to take recap. So what I was talking was, so this, because of the internet expansion and the geographical expansion, we were we were able to create another systems, basically the warehousing systems. The warehousing systems were created for the core purpose that, I decouple the actual production operational databases with the warehousing databases. When this decoupling is happening, then we can say that you will be able to do your analysis on your data warehousing systems instead of running your queries on the actual operational data stores. So because it reduced a lot of burden on the operational data stores, and it also gave a lot of flexibility for running the analytical queries on warehouses. You could run throughout the day. You do not have the problem of only running in the night. So that has actually given a lot of benefit. And the second one, which I was talking, is also the ability to store historical data. Data warehouse has this great ability to store historical data where you can do the comparative analysis between your previous year's data, like how the business performed 2 years back, how the business performed 5 years back, and comparative analysis like 5 years back, how was the business and how is it right now, right? So you could do all this kind of analysis, and then based on that, you were able to create much more richer analysis of your data, right? So these were the good things of data warehouse, and data warehouse is very, very powerful tooling. Even in today's date, we do see that there are a lot of data warehousing systems available. People are still running a lot of reporting jobs and all that batch processes on data warehouses. The only downside data warehouses saw in the recent years, I would say recent instance like 10 years back, around 2012, 2014, that time frame, is the new term which is called as big data, which came into picture. Now, when big data came into picture, big data was predominantly unstructured in nature, and data warehouses were typically structured in nature. So because of that, the only thing which these data warehouses were not able to cater were catered by something called as data lakes. Right? So data warehouses were typically in this kind of a structured nature where they have row column based tables and structures. But if, for example, say images came into picture, for example, say text or videos or sensor based data or like any other kind of unstructured or semi structured information is gathered, then the data warehouses were not the real suited databases. So there were other kind of databases which are required. So if again I recollect back in the year 2012, 2014, that time frame, where there was huge advancement in the uh, big data community, where people try to capture, so that there are terms like 4Vs and so on, like there was huge volume of data, variety of data, and the veracity of data and all that stuff came into picture. But predominantly the focus was like, okay, I have this structured information, but if I also have unstructured information, it can be information from our sensors, it can be IoT connected devices, it can be images of MRI scans, it can be videos of a surveillance camera, it can be a lot of textual information of a policy document or a legal document and so on. So if you see, uh, our typical data is not only like a structured in format, it also has a lot of unstructured nature in. So there are videos, there are images, there are text, there are sensor information, there are semi-structured kind of information and so on. And that's when the big data came into picture. A lot of adoption happened in the big data space. And typically the Hadoop systems were created. The open source Hadoop systems from Google were invented, and they were adopted by enterprises. And if you see in the recent years, from 1 2 years, we are seeing a huge adoption in generative AI. And because generative AI is hugely dependent on multimodal data, multimodal in sense images and videos and text, all of them combined, companies which has invested 10 years back on big data systems and they've stored that big data for these all these years are hugely benefiting from the generative AI. Right now, people are just thinking that, okay, how can I use the generative AI? How can I fine tune systems? How can I, make use of this, get ROI out of this? All these all these things are coming right now, but people who have already invested for those many years, right, close to 10 years now, collected huge wealth of data, those are the ones who are reaping huge benefits because they already have available data, high quality data, indexed data. There is a lot of metadata available for the data. You can easily use that information to either fine tune or create your own models which can help do a lot of automation in those industries. So I have worked with a lot of industries like banking, then insurance, travel, transport, and hospitality. So and even retail. So all these industries started working on big data somewhere around 2012, 2014, 15 time frame. They were focused on storing large volumes of images. For example, if you talk about banks were storing large volumes of check data, transaction data. There were informations of large volumes of texts. For example, call center information was converted into voice was converted into text, and the text was stored for a large proportion. So if I have this call center information, the lot of voice-based recording information, lot of text-based information is available, it becomes very easy for us to do the processing and can use the wealth of data. So that's what is happening, and you are seeing companies which have actually used that information benefited a lot. Now, how are these data lakes created? So data lakes created predominantly on open on-prem based systems like Hadoop. They have created their own Linux based systems. They have created Hadoop servers on that, and multi cluster environments were created to store these large volumes of unstructured data. But thanks to cloud computing, if you see in 2015, 18 time frame, there was huge adoption of cloud environments. The first adopters of cloud was AWS cloud, then came Azure, then came Google cloud. But thanks to these cloud systems, what happened is the storage and the compute become very cheap. So companies were not really worried about investing huge volumes of storing huge volumes of data because the cloud was very quick and easy to adopt. It was easy to implement, and the pricing was also within the limits. If, for example, we say a company has to set up a multi-gigabyte or multi-cluster data center for themselves, it becomes a tedious task for them to ensure that the systems are up and running, to ensure that the batching is happening on the servers, there is no vulnerabilities on the servers. So all that stuff becomes a very very tedious tasks. So 50 years back, which was a bigger problem, 30 years back, which was a bigger problem, 10 years back was resolved because of cloud computing. And thanks to AWS, Azure, or Google Cloud, it has created so easy way of adoption, especially for large volumes of data storages, large volumes of data compute, large volumes of data processing. All these things came into picture, and because of that, huge data was stored. Now we came somewhere around 18, 19, that time frame where we are able to store large volumes of text, images, videos, and all that information. Then the adoption came for doing large volumes of analytical projects, is typically getting into some kind of machine learning, some kind of data science related work, and so on. But before doing that, people started thinking that what is the data stored? They were storing huge volumes of data, but they need to understand what was the data talking about. So first set of projects which were involved was to doing a lot of EDA. EDA is nothing but exploratory data analysis. The lot of analysis is done to see like what the data is talking about. If you are able to look at different tables, can get insights from the different tables, and can get the observations of the tables, then half of the problem is solved. The issue is that we do have lot of data, but we are not able to make sense of this data. We do not know what is the relation between one table and another table, what are the different columns talking about, and how are they related to each other. So that's where the data exploration comes into picture. There are a lot of tools which were implemented. You could do a lot of exploration using core Python, or you can also use a lot of publicly available tools like Tableau or ClickView or Power BI. So these are some of the popular tools which were used for doing something called as data exploration and data visualization. So once we do this data exploration and visualization, you will be able to understand that what is data trying to talk. So we will be able to understand the patterns of the data. We will be able to relate data components together. We will identify which of the features are having rich information. And then based on those features, you will be able to gather information. So data exploration was one of the core components of entire AI processing. Once the data exploration is done, then people created something called as feature marts. Now, in typical machine learning and AI studies, we generally talk about modeling as a central piece, but a lot of these additional things are very, very important, because once we do data exploration, once we look at different patterns of the data, we need to store those patterns. We need to uh, create those transformation functions and store that results in something called as feature marts. In AI terms, we also call it as feature stores. Now, feature stores are nothing but these are the reusable features which can be used across the functions by the data scientist. Imagine I am doing analysis on loan prediction, and I am a data scientist who is working on the loan prediction. I try to do a lot of exploration of data. I try to combine multiple tables. I try to get the nitty-gritty details of each and every table, and then I create this golden data set. And this golden data set is the aggregated version of all customer information, which is very, very suited for loan prediction. Imagine that analysis I do a lot of outcome, I do a lot of predictions. But if I let that data go, then somebody else who is taking my job role at a later point of time will again have to redo all this effort to reduce, or to reduce the rework, or to reuse the uh, analysis. People have created something called as feature marts. Feature marts or feature stores. So feature stores, if I tell in a simple terms, this is nothing but any data scientist does the data transformations, try to create some kind of features. Those can be stored in these feature marts or feature stores, so that other data scientists can make use of it and can speed up the entire end-to-end AI/ML processing at a faster pace. The major issue in those years was, how do I speed up this AI/ML process? Even now we have this major problem that the experimentation to productionization has to be done in a much faster way. Experimentation is done maybe in your local laptop, or on your development machines, but most of the projects die at the experimentation phase. The core business will be able to generate revenue only when the experimentation is converted into a business problem. So feature marts have become very, very core components in which the feature transformation happens. And the feature transformation, there are other terms like feature discovery, feature hydration, and so on. Feature discovery is nothing but other data scientists wanted to search like what are available features, what is the metadata of the features, how are they helping, and all that stuff. Then the feature discovery will be able to help to identify the right set of features for their experimentation. So imagine I did the feature transformation and I created a feature called as my average monthly balance. So this my average monthly balance need to be discovered by other data scientists so that they can directly use that feature and can use it in their experimentation phase. Feature hydration is nothing but the way in which you can perform these jobs, you can condense the information and create the features. So once the exploration is done, once the feature creation is done and the information is stored in the feature marts, the core component comes into picture where we do the modeling. Now, modeling again, I'm not going into deeper modeling techniques. There are a lot of deeper modeling techniques in the supervised modeling, unsupervised machine learning, reinforcement learning, and even now we have deep learning techniques, generative AI techniques, LLM creations, and all that stuff. I'm sure throughout this week you might have learned a lot of things about all these things, but this, as you see, it is only becoming a smaller piece of the equation, and I will talk about all other terms also, which are essential for creating an end-to-end AI/ML project. I'll talk about those things also, but this becomes a small piece of the bigger equation. Now, the modeling is where it talks about how do I create a model, a predictive model using a lot of ML techniques, in which the data which is transformed can be used as an input and we can condense that information in a predictable outcome. So once we condense that information as a predictable outcome, any future information which is passed to it can generate similar kind of outcomes. So we are trying to create something like a predictable model where given any information to this model, it will be able to do some kind of prediction. It will be able to give some kind of results. So within the supervised machine learning, there are a lot of techniques. For example, there is classification techniques, there are regression techniques, and so on. Classification talks about how do I classify a outcome into one or the other classes. For example, the example of talking about loan prediction, whether I can give a loan or not, is a classification problem. So the possible outcomes could be, yes, I can give a loan. No, I should not give a loan. Probably I should put the case on hold or for further verification and so on. So there will be 4 or 5 different classes which can be as an outcome for a given prediction. So customer comes for prediction, customer comes for an application of a loan, then he provides all the details like what is his age, what is his bank balance, your liabilities, whether he's married or not, whether they have any kids or not. So all this information becomes the features, and all those features will help us to do the prediction, which is a classification problem, and we are trying to predict whether he can get loan or not. Similarly, there are other set of algorithms called as regression algorithms, which will be used for doing more of a continuous value prediction, where we are trying to identify a numerical outcome. Where I say like, okay, loan approved or not is a classification problem, but how much loan should be approved? It should be like, say like 2,50,000 loan. So that number term get into something called as a regression problem. So we are trying to predict like how much loan is approved. So as an end outcome of a product, we will have 2 algorithms which are doing predictions. One is predicting whether a loan should be approved or not. The other one is predicting how much loan should be approved, and outcomes of both will be fed to another model where it will compile an email and it is sent to a customer. At the end, the customer will get an email saying that congratulations, Sitaram, your loan is approved and you will be getting 2,52,000 and click here to apply, something like that. you'll get an email. So where we are seeing there are multiple algorithms which are used, the supervised, unsupervised, reinforcement learning. We will not get into deeper things of it, but here we understand that this is where the data scientist will be doing a lot of experimentations. So once the data scientist completes the experimentation, the next step is like, how do I deploy this model into a real production or real executable? Now that is done in two modes. One is called as a batch mode of deployment. Second one is called as an online mode of deployment. So the batch mode is nothing but there are jobs which run. For example, you do a model which basically trains the data over time, and you can create the executable model, and we will run this as a batch job. Imagine every day there are 100 applications for loan. So these 100 applications will be fed into a batch job, like a Python program which is run on a scheduler. And this Python program, what it will do is it will every day it will run say at say like 9 o'clock in the evening, and it will predict whether out of the 100 applicants which are applied in that day, how many applicants are approved, how many applicants are rejected. So this is happening in a batch mode. So there is a program which is collating all the applicants and then giving it to this prediction program, and then this prediction program can be again have a downstream job which basically sends email to approved customers and rejected customers. Approved customers will get email saying like, congratulations, your loan is approved, this much loan you're getting, and so on. And rejected customers will get like probably the reason for it. It might give like your credit score is low, or your liabilities are higher. We regret that your application didn't go through, but it can give other kind of recommendations saying that you can apply for something else and so on, right? So this is entire batch system which is created where the central piece is where it is doing the prediction, but there is an upstream and the downstream, and it works in the batch mode. So batch mode happens like this. So you have the model which you are trying to take it from the cloud. You will invoke the model from the cloud. We will use tools like, frameworks like Django. We have frameworks like Jenkins, and the entire stuff runs on a Kubernetes Docker container, and it connects to the cloud system, do the prediction, get the results in the batch mode, and gives the results. So batch mode is predominantly, if you see, most of the AI models run in a batch mode. People say that they will do online-based prediction, REST-based prediction, but if you ask me, 80% of the models run on batch-based analysis, so batch-based coding, and predominantly that is used in the regular real world. Online mode is via an API or a REST-based environment. So imagine you have a website or maybe a mobile app, and then you can log into abcbank.com and you get a page for applying for loan. You can fill in all the details, the age, bank balance, and all other details, and then say submit. Once you click that submit button, which invokes a backend model. Now this is an online mode. We can also call it as a REST-based deployment. In these REST-based deployments, what we do is the model is condensed as an API call, and the front-end systems can invoke these APIs, which internally will call the model and can get the results. So the abc.com, you can log into it. You will be able to get the front-end page. You fill in on all the details and then click on the apply loan button. It will invoke a model in the backend, and it will give instantaneous results, right? So it is like the ChatGPT kind of an interface, right? So ChatGPT works on this REST-based deployment. So you have an API, it will be accepting certain kind of prompts, it will be accepting certain kind of API parameters, and then invoke the model in the backend. It will condense the information, and you get the response in a real-time mode. If you're asking a very heavy loaded question, it might take a little time, but you can also stream the results. So there are also options in which you can say like, okay, I want to get my results in a streamed fashion. So as and when you can invoke the REST API, It will be able to get the response, and as and when it gets the chunk by chunk information, it can stream the information back to the front end, and then you'll be able to render it to your front end, saying that, it doesn't wait for the complete information to be fed, but as and when you get the first chunk, second chunk, third chunk, you'll be able to printing that information. So this kind of models are called as REST-based models or online-based deployment. And then predominantly we will deploy this for use cases. But if you ask me how many such kind of, if you take 100%, there will be 20 to 30% of the models which will be invoked in the REST mode. But most of the models will be invoked in a batch-based mode. Right? So that is the example of it. So once the models are deployed, once the models are available in production, the next important thing is to understand the goodness of the models and understand how well these models are performing. Are there any changes in the models, or are there any changes in the data? So for that, we create something called as monitoring systems. So we have model monitoring systems typically used for monitoring the goodness of the models. For example, in starting of the year, January, I have deployed a model. And I wanted to understand like how the model performed over the time. How was it performing in February? How was it performing in April? How was it performing in October, November, and so on? So I wanted to understand over the time, are there any problems? Are there any issues? Was there is a change in the data? So there are different type of drift metrics which are captured. For example, there is something called as data drift, there is something called as model drift, concept drift, and so on. But basically what we're trying to understand is the distribution of the data changed, or is the performance of the model changed, or is there any reason for which we need to re-invoke or do retraining, right? So there is something called as auto retraining, where we try to capture different parameters of this monitoring, and based on the parameters, if they go beyond certain thrift levels, then we can trigger an auto training job which captures all the latest data and then retain the model on that latest data. So all these things are important because many times we were told that we can open some notebook, Jupyter notebook or Google Colab notebook, and then do some training testing of the model, get some accuracy score, and we are done. But that is not done. It is only one small piece of the equation. We need to see like how these models can be monitored over time. How do you gauge the performance of the models? How do you gauge the accuracy of the models over time, right? And then comparatively, how we can auto tune them so that they continue performing the way it is expected. There are two major important metrics which are used in this monitoring phase. First one is called as explainability. Explainability talks about how is your, based on what kind of information is your model providing the outputs. So it should be able to give some kind of guidance based on which it has taken so and so decision. For example, if I'm approving a loan or rejecting a loan, I should have a clear cut information like why did I approve loan or why did the model rejected the loan. It should be able to explain. There are a lot of these metrics which we will calculate internally in the model monitoring metrics, where we try to capture all these information, where we are trying to see like how good is the model. There are CSI scores, PSI scores, different kinds of vanity metrics are calculated, which will tell that the model has taken so and so decision based on all these parameters. Right. And many times, and specifically in banking, we do see that there is a lot of legal and compliance issues. There is a lot of governance needs to be done, because we need to be liable for the decisions made by the model. If at all some clerk or some guy makes the decisions, it is very easy because you can go and ask the clerk saying that, by what reason did you approve or rejected the claim or rejected the loan application, then it will be very easy for them to respond. But if the model takes the decision, it becomes very, very tough. So that's the reason explainability becomes a very crucial piece of information. The second one, which is also very important, is the fairness component of it. Now, the fairness talks about the goodness of the model, irrespective of the demographics, irrespective of any of the considerations with respect to age, caste, creed, gender. So, irrespective of any of those parameters, the model should behave in the same way. For example, I am applying for a loan, and then my wife is also applying for a loan. And imagine both of us have same educational backgrounds, both of us have similar kind of job profiles, both of us have same age, similar bank balance, and all that stuff. But I get more loan and she doesn't get the same amount of loan which I have got. That means that the model is biased. So model will be biased because the amount of data we are feeding to the model is also having such kind of biases. So it biases creeps in because the data which is provided to the model is also having these biases. So we need to tone it down. We need to ensure that the models are not biased. They are unbiased, irrespective of, like, say, gender or caste or creed or financial status or whatever it is. So based on all these informations, we will try to uh, calculate these fairness metrics. Again, the fairness metrics are calculated with respect to open, equal opportunity, and different parity-based metrics are there, which will try to identify whether the model is unbiased and giving results as expected. So when there is a bias coming up, we try to justify the data. We try to check the data, and then we try to pump in data so that the model is trained in a fashion where it is not biased with any input data. So we do a lot of those kind of techniques. So once the modeling is in place, so your deployment is running either in a batch mode or in an online mode, so the REST-based models are there, then correspondingly there will be these monitoring jobs which will be running. Imagine there is one job which is a prediction job or a scoring job which is running. Parallelly, there will be a monitoring job which will run, which will monitor the goodness of the prediction job. So it will monitor, you can monitor on a daily manner, you can monitor as a scheduled weekly manner, or maybe a monthly monitoring system. So depending upon the requirement, you will try to schedule the monitoring jobs also, and it will capture all those metrics and then provide in a dashboard. So we also have created dashboards which can show all this information: how many jobs are there, how many predictions are happening over time, what is the monitoring metrics of those jobs, and how you can compare them, and how you can determine the goodness of those models. Once that is done, the last piece of the equation is to create more standardized protocols. So we have two other important systems which is used in the entire AI ML journey, is called as how do you create AI governance and how do you create your quality assurance, or basically the AI testing. And many times people are very fancy about getting data scientist jobs, but there is a huge ecosystem around data scientists. If you see on the left side of this graph, we have huge data engineering professionals. So in India, there is a lot of data engineering roles which are available. There's huge volumes of data engineering capabilities because we need to transform the data and make it available for the data scientists to consume. So there is a huge amount of work there. That is where there are a lot of jobs. On the right side also, we have huge number of jobs with respect to ML engineers, or what we call as ML testers. So ML engineers are the ones who are responsible for productionizing your ML jobs. So data scientists will work on notebooks. They will work on your experimentation environments. They create your models, but these models can only be deployed by your ML engineers. They are the, again, lot many jobs are there where they are the ones who are responsible for doing either a batch or online based deployments. They are the ones who are creating your monitoring systems. They are the ones who are creating your end-to-end pipelines, API creations. All that stuff is happening by the ML engineers. And there is also another set of engineers who are called as ML testers, and they are also very in huge demand because traditional testing mechanisms, traditional quality assurance mechanisms were focusing on something like an API testing or Selenium and those other methods. But there are not many people who know how to test an AI model. For example, how an AI job works, what are the different pieces of information are required, how do I create test cases for an AI model, what type of data needs to be ingested, how do I create what we call as synthetic data. So all these are huge requirements for an AI company. And when we have to do all these things to ensure that the model is giving the best of the best results, then we also need these AI or ML testers. So, earlier in 2021 time frame, we were the first companies to also invest having AI testers in our entire ecosystem, so that we can create the AI models at the pink of the health, right, to the best quality and so on. Now, coming to the AI protocols, like what all the things which are required for the AI testers or quality assurance engineers is like to do something called as synthetic data generation, to do something called as exploratory analysis, to do something called as test case generation, test case creations, and so on. And nowadays, people are also using generative AI for creating all those things. So generative AI is used left, right, center for uh, for um, for creating a lot of these test cases. You can create user stories. You can also change the acceptance criteria. You can create something called as test case generation, and also execution of the test cases is also being automated by generative AI. So we are seeing that this particular field is also revolutionizing the way in which a lot of work is happening in and around AI and ML. But it's a very important work. Other piece in the AI protocol is the AI governance. Now, it is very important for us to keep the entire AI/ML lifecycle in a proper governance phase, because these are experimental in nature. Predominantly, most of the companies just think AI and data science projects as an experiment, but they have huge potential of generating revenue, and if they are tracked from start to end, then it will be very productive in generating a lot of ROI. Now, the way it can be done is, how do I create an end-to-end governance portal in which I capture like what are the use cases, I capture the hypotheses which are required for a specific analysis, I capture the experimentation results. For example, how many experiments are done, which models were used, how different models are performing in different environments, how are the metrics calculated. So in AI governance, we use, for example, tools like ML Flow for capturing the model metrics. We use a lot of homegrown systems which can capture the use cases, which can capture the hypothesis testing, which can capture the approval systems between environments. For example, I do experimentation in a development environment. I will compile all the results. I will post all the model metrics. I will post all the I will post all the test results and all that stuff, and then I can go to the next phase. Like I can go from a development environment to a QA environment. I can go into a UAT environment. I can go into a staging environment, and then go to the production. So there are different phases in which the experimentation happens, and there should be a proper governance frameworks in place which can capture like what was the idea, what will be the ROI, what hypothesis was done, what experimentation was done, what were the results, and what type of approvals are required, which data has to be which data has to be used. All that stuff has to be in one single portal. So we have a similar portal which basically does the AI governance, and it can give like end-to-end visibility of your AI experiments, to which phase they are in, what experiment stage they are in, what results they are developing, and how much revenue the model is being generating, and all that stuff will be in one single portal. So that talks about the AI governance. So if I can give a slight recap of what we have discussed. It's been like more than an hour or so now. So what we are discussing in this entire slide is basically to understand that over the years how the data analysis transformed, how the AI models were developed, like right from the ODSs, getting into data warehouses where a lot of analytical queries used to be run. Then came the data lakes where a lot of volumes of data was pumped into it. We created systems on cloud environments. AWS, Azure, and Google Cloud were the pioneer ones. Now the data was pumped into it. Then we did a lot of analysis on exploration. We try to understand different patterns of the data and all that stuff. Then we created reusable components of our data in terms of features. Those features were stored in feature marts. Then those features were used for doing experimentations using models. There are supervised models, unsupervised models, reinforcement models, generative models. All those models were used for creating your experiments, and those experiments were deployed either in a batch mode or in an online or a real-time mode using APIs. And then we also created systems for monitoring, especially the goodness of the models, managing the drifts between the models or between the data, and so on. We also worked on creating explainable fair systems. And then finally, we looked at like how do you create these end-to-end AI protocols, both from a governance standpoint and also a quality assurance standpoint. Governance standpoint talks about creating an end-to-end pipeline, showing a visibility for for most like senior executives to see like where these models are, how much revenue we're generating, and all the legal and compliant related information. And the quality assurance part is where we are talking about how the models can be created and tested in a much more faster manner, right? So I think that is what I wanted to share today. If you have any questions, I'll be happy to spend 10 15 minutes on that. If not, we can close it. Dr. Papia, do you have any questions?
Okay, I think someone is having some question. I just will unmute him. Prashant Kulkarni, sir. Okay, fine. We are allowing mic to you. Yes, kindly ask your question, sir.
Good evening, sir.
Good evening, sir.
Actually, in these data processing models, actually the security aspect is not considered at all. So, which entity is actually responsible for security aspect? Because data we are analyzing, but whenever we share the data, what is the security? How the data is secured?
Yeah. Sorry. So I didn't talk about that piece. So security aspect comes at the engineering level only, data engineering level. So what happens is, so we also have something called as metadata and data security frameworks, which are created. Primarily, they are not the AI data scientist's job, but they are that is the job of the platform engineers. Basically, we have to create metadata management and also data security management. So in data security management, we talk about two things. First one is the data security and the application security. So data security talks about when I'm storing the data, what all features, what all columns have to be PII information, which all columns need to be encrypted, which all columns need to be open. So all that information has to be done. So we have framework for that. It comes at the data engineering level, this space.
Okay, sir. Okay. Thank you, sir.
If you have any further question, I can go a little deeper and talk about it. But yes, so there is two angles to it. One is the data security and also the application security. Data security talks about how do we govern the security aspects of the data, who can access the data, what data has to be shared within, for example, I can see customer data, but I can't see their their salary information or their investment information. Similarly, across domains, for example, the consumer banking is one domain, there can be investment banking another domain, there can be marketing domain, there can be sales domain. So cross domains also we can't give data access. So there will be portals which govern the security of the data, who can see the data and what accesses they have and role based accesses. So all those things will be governed there. So that is one angle. There is also application level security. So what applications can be viewed by which people? So because all these there are different platforms which are created, right? And there are different applications which are created for this. So applications also have secured accesses. So we need to govern both application access, application security, as well as the data security. So both will be treated in the similar lines. Got it?
Yes, sir. Yeah, yeah. Thank you.
Okay, any other participants having any query? Okay, fine. I think then we have concluded the session. So I request Dr. Satyabrata Singha sir to propose the vote of thanks.
Yeah, good evening, everyone. It is my privilege to extend our heartfelt gratitude to Mr. Sitaram Tirupalli sir, Vice President of ML Engineering, for delivering an exceptional session on AI operation in the real world. It is the final technical session of this 6 days long FDP. Mr. Sitaram sir, your session provided invaluable insights into the practical aspects of deploying AI systems in real world scenarios. The clarity with which you explained the challenges, strategies, and best practices of AI implementation was truly remarkable. Your wealth of industry experience has offered us a pragmatic understanding of how AI solutions are shaping the future across various domains. On behalf of the organizing committee and all the participants, I sincerely thank you for sharing your expertise and making this final session a fitting conclusion to our FDP. Your contribution has been instrumental in bridging the gap between theoretical concepts and practical applications of AI. To all the participants, thank you for your enthusiasm and active involvement throughout the FDP. Let us carry forward the insight gained and strive to make this meaningful contribution in the field of AI and beyond. Thank you once again all, and we look forward to future collaborations and continued learning from together. Thank you.
Thank you, Dr. Singha. So finally, we marked the end of this interactive sessions. There were 13 very extensive, very interactive, and very informative sessions in this faculty development program on all these 6 days. Thank you all the participants for patient hearing, skillful questionnaires, and proper visibility regarding the program. So now let's mark the beginning of the valedictory session. So good evening to all.
Shubhodip sir, just wait. We'll just wait for 5 minutes for our chief guest to arrive. Then we'll start the session. Okay, sir?
Sure, sure, ma'am.
Just 5 minutes. Satyabrata sir, please play the department video in the meantime. Very soon we are going to start with the valedictory function, and thereafter we will inform about the examination, assessment timing and date. Okay, so just be online, all the participants. Dr. Kannan sir, can you please check your mic is you can unmute yourself?
I hope so, madam. Is it audible, ma'am?
Yes, sir, it is audible, sir. And Venugopal sir, also please check once. Venugopal sir, kindly unmute yourself.
Venugopal Reddy Garu, an eminent educationist with a social conscience and commitment. It has grown in its size and stature over the years from an initial intake of 240 to 1,308 students. VIT is one of the largest engineering colleges in Telangana. The institute is affiliated to AICTE and JNTH and accredited by NAC and NBA for ECE, EEE, CSE and ME department. Electronics and Communications Engineering Department was established in the year 2001 as one of the prime branches at Bharat Institute of Engineering and Technology. It is currently running undergraduate, that is BTech, and postgraduate courses in embedded systems, VLSI technologies, and wireless mobile communications. The course was accredited by National Board of Accreditation in 2007 for a duration of 3 years and second time accreditation in 2019 for a duration of 3 years for the academic year 2019-20 to 2021-22. The department has highly experienced former scientists and engineers from R&D who have headed national reputed laboratories like DLRL, DRDL, BTL of DRDO. The department has 47 experienced and well-qualified faculties at present. The department has also shown excellent achievements in terms of research publications, patents, and organizing workshops, faculty development programs, and conferences. Further, it has active IETE and ISTE chapter. The students of the department has excelled in Chhatra Vishwakarma Award in regional level and national level. The students of EC department have also showcased their talent in Smart India Hackathon and BIT Hackathon. One of the team was shortlisted among top 20 in national level IBM NASCOM Hackathon at the national level. The EC students were the winner of hackathon conducted by Hyderabad Police. Besides, the students and faculties have excelled in NPTEL certificate courses. The vision and mission of the department aims at quality teaching and building a good academic and research environment. The use of various instructional methods and pedagogical initiatives are taken up, such as project-based learning, smart classroom, ICT-supported learning, and so on for the teaching-learning process. The students also attend industrial visit in industries such as ISRO, Infosys, and so on. The students are given hands-on training for understanding the subject more efficiently. The department has a good alumni association of the pass-out students working in various renowned industries and organizations. ECE department has received many grants and funded projects from AICTE, DRDO, and UMBA. The faculty development programs are organized from time to time for making the faculties aware of the latest technologies. Experts from industries and IITs, NITs, DRDO visit the institution to present guest lectures and conduct workshops. Besides regular laboratories in the course curriculum, the department has advanced laboratories, equipments, and softwares like MATLAB, Mental Graphics, and Spectrum Analyzer. The ECE department has also undergone various Unnat Bharat Abhiyan activities and visited the nearby villages and provided facilities. During pandemic, the department has provided sanitization kits to migrant workers. Bharat Institute of Engineering and Technology has a strong tie-up with renowned industries and organizations. The Department of Electronics and Communication has a good placement record throughout the years. Besides teaching and co-curricular activities, we have various clubs like Hackathon Club, Singing Club, Dance Club, Sports Club, and so on, in which the students participate and rejuvenate themselves. Bharat Institute of Engineering and Technology, established in 2001 by Chinta Reddy Madhusudan Reddy Educational Society under the leadership of Sri C.H. Venugopal Reddy Garu, an eminent educationist with a social conscience and commitment. It has grown in its size and stature over the years from an initial intake of 240 to 1,308 students. BIT is one of the largest engineering colleges in Telangana. The institute is affiliated to AICTE and JNTH and accredited by NAC and NBA for ECE, EEE, CSE and ME department. Electronics and Communications Engineering Department was established in the year 2001 as one of the prime branches at Bharat Institute of Engineering and Technology. It is currently running undergraduate, that is BTech, and postgraduate courses in embedded systems, VLSI technologies, and wireless mobile communications. The course was accredited by National Board of Accreditation in 2007 for a duration of 3 years and second time accreditation in 2019 for a duration of 3 years for the academic year 2019-20 to 2021-22. The department has highly experienced former scientists and engineers from R&D who have headed national reputed laboratories like DLRL, DRDL, BTL of DRDO. The department has 47 experienced and well-qualified faculties at present. The department has also shown excellent achievements in terms of research publications, patents, and organizing workshops, faculty development programs, and conferences. Further, it has active IETE and ISTE chapter. The students of the department has excelled in Chhatra Vishwakarma Award in regional level and national level. The students of EC department have also showcased the talent in Smart India Hackathon and BIT Hackathon. One of the team was shortlisted among top 20 in national level IBM NASCOM Hackathon at the national level. The EC students were the winner of hackathon conducted by Hyderabad Police. Besides, the students and faculties have excelled in NPTEL certificate courses. The vision and mission of the department aims at quality teaching and building a good academic and research environment. The use of various instructional methods and pedagogical initiatives are taken up, such as project-based learning, smart classroom, ICT supported learning and so on for the teaching learning process. The students also attend industrial visit in industries such as ISRO, Infosys and so on. The students are given hands-on training for understanding the subject more efficiently. The department has a good alumni association of the pass-out students working in various renowned industries and organizations. ECE department has received many grants and funded projects from AICTE, DRDO and UMBA. The faculty development programs are organized from time to time for making the faculties aware of the latest technologies. Experts from industries and IITs, NITs, DRDO visit the institution to present guest lectures and conduct workshops. Besides regular laboratories in the course curriculum, the department has advanced laboratories, equipments and softwares like MATLAB, Mentor Graphics and Spectrum Analyzer. The ECE department has also undergone various Unnat Bharat Abhiyan activities and visited the nearby villages and provided facilities. During pandemic, the department has provided sanitization kits to migrant workers. Bharat Institute of Engineering and Technology has a strong tie-up with renowned industries and organizations.
Okay, Shubhari sir, please start.
Okay, ma'am. Good evening to all the respected dignitaries, participants, my dear colleagues who are attending here in this 6 days online AICTE FDP on AI and quantum computing, the future of intelligent systems. We have come to the end of our journey. This is the valedictory session. Already we had very intensive and enriching 13 sessions, and we are all set to commence our valedictory session. So it's my honor and privilege to deliver this speech as we draw close to this meaningful faculty development program. Over the past few days, we have come together as a community of educators, sharing knowledge, exchanging ideas, and enhancing our understanding of crucial subjects that will undoubtedly enrich our teaching methodologies as well as academic practices. So, firstly, let me begin by extending my heartfelt thanks to all our distinguished guests who have graced this occasion. I would also like to thank the convener of this FDP, Dr. Papia Datta ma'am, and I would also like to welcome her for an insightful summary of the FDP, which shall remind us of the breadth and depth of the FDP's achievements.
Thank you, sir. Very quickly, I'll just go in brief the summary of the 6 days of the National FDP. Before that, good evening to our respected dignitaries, Honorable Chief Guest, Colonel B. Venkat, sir. I hope I'm audible to everyone.
Yes, ma'am. Yes, ma'am. Audible.
Okay. So, a very good evening to our respected dignitaries, Honorable Chief Guest, Colonel B. Venkat, sir, Dean Admin, Dr. V. Kannan, sir, and Dr. Venugopal Kunal, sir, for Principal BIT. Professor G. Kumaraswamy, sir, Director BIT, and participants throughout the country. First and foremost, I would like to extend a warm welcome and express my heartfelt gratitude to all our distinguished guests for joining us today. I would also like to welcome and thank our wonderful participants who participated in these 6 days of FDP with a lot of patience and enthusiasm. I would like to give a brief summary of these 6 days of the National FDP conducted on AI and quantum computing, the future of intelligent system, sponsored by AICTE Atal Academy. On the day one, session was taken by Dr. Debashish Das from IIT Jodhpur. The session was on the quantum-driven future intelligence rapid response system. He likely focused on the integration of quantum computing with artificial intelligence to create a highly responsive system capable of processing and analyzing large datasets in real time. Next session on day one was taken by Dr. Shuman Dev from NIT Agartala. His session on quantum computing, quantum image processing provided a comprehensive overview of how quantum computing principles can revolutionize image processing tasks. On the day two, the session was conducted by Mr. Sitaram Tadepalli, Vice President ML Engineering. His session focused on explaining artificial intelligence AI in a simple and accessible way while exploring its current applications, challenges, and potential future impact. The session aimed to bridge the knowledge gap for both technical and non technical audiences. The second session on day two was conducted by Dr. Debashish Das from IIT Jodhpur. He delivered an insightful session exploring the convergence of generative AI with edge intelligence, highlighting how these two cutting edge technologies can complement each other to enable innovative applications. The session focused on the technology's potential, challenges, and future outlook. On day 3, the first session was conducted by Dr. Yogan Jayakumar, Associate Professor, Technical University, Malaysia. His session was on AI and data analytics. He covered the topics on Introduction to AI and Data Analytics, Emerging Trends on AI, application of data analytics, challenges and ethical considerations, and future directions. On day 3, second session was conducted by Mr. Vidyasagar Tejamurthala, Principal Architect, Zelis Healthcare, on intelligent app development leveraging generative AI. He focused on how AI and data analytics are reshaping industries and opening new opportunities. Generative AI tools like Copilot significantly enhance development speed and efficiency. On day 4 of the FDP, the first session was conducted by Mr. Rohin Koduri, scientist from DRDL. His session was on AI's transformative role in defense. Mr. Koduri emphasized how artificial intelligence is revolutionizing modern defense systems, enhancing decision making, operational efficiency, and situational awareness. On day 4, the second session was conducted by Dr. Abhinav Kumar, professor from IIIT Hyderabad. His session was on role of quantum computing and AI in the next generation communication network. Dr. Kumar discussed how quantum computing can significantly enhance the capacity, security, and efficiency of the communication networks. The day 5 was marked by the session of Dr. Sivakumar Subramaniam, Technical Project Manager, IIoT SME. His session was on leveraging AI for enhanced IoT deployment, key applications, and features. Dr. Subramaniam described how AI amplifies the potential of IoT by enabling intelligent data processing, real time decision making, and predictive analysis. The second session on day 5 was conducted by Dr. Shuman De from NIT Agartala. His session was on quantum automated object detection. He focused on quantum computing and traditional object detection, quantum algorithms for object detection, and applications of quantum object detection. He explained that by harnessing the unique properties of quantum computing, we may see substantial improvements in the speed, efficiency, and accuracy of object detection tasks in the future. On the final day of the FDP, there were 3 sessions. The first session was conducted by Dr. Anish Chivukala, Assistant Professor, BITS Pilani, Hyderabad. His session focused on quantum computing, basics quantum machine learning models, quantum speeder for machine learning. He concluded that quantum machine learning holds tremendous potential to transform fields ranging from artificial intelligence to data science. The second session was conducted by Dr. Abhinav Kumar, professor from IIT Hyderabad. His session was on the integrated sensing and communications with quantum compute and AI in beyond 5G networks. He gave a brief idea on integrating sensing and communication, quantum computing in ISAC and beyond 5G, AI and machine learning in ISAC. He concluded that the integration of sensing and communication systems with quantum computing and AI in beyond 5G networks offers a transformative vision for the future of wireless communication. The third and final session of the FDP was conducted by Mr. Sitaram Tadepalli, Vice President from ML Engineering. His session was on AI operations in the real world. He discussed on retail and e-commerce, manufacturing and industry 4.0, smart homes and Internet of Things. Finally, we have concluded this 6 days national FDP, and in a nutshell, we can conclude that AI is already transforming the real world across various sectors from healthcare to finance, agriculture, and manufacturing. As AI technologies mature, they will continue to automate and optimize processes, improve decision making, and create new opportunities for innovation. Almost 340 participants joined in this FDP program throughout the country, and I hope everyone enjoyed all the sessions in this FDP and got more insights and knowledge on this topic. Thank you. Thank you for this session and participating in this FDP to all the participants and to all the resource person, and my most sincere thanks to today's honorable chief guest. Thank you.
Thank you, ma'am, for your nutshell summary. I hope the participants also have recapitulated the things that they have learned in these 6 days. So now I would like to welcome Dr. V. Kannan, Dean Admin and Professor of the Department of ECE, BIT, for his inspiring welcome speech. Sir, your words shall encapsulate the vision of fostering academic excellence, which served as the cornerstone for this program. So let's welcome Dr. V. Kannan, sir.
Yeah. Our most respected Honorable Chairman, sir, Chief Guest, can be
Yes, I have made you gave you the access of mic. Please,
Ma'am, is it audible?
please continue, sir. Sorry.
Is it audible, ma'am? It's audible now.
Yes, sir, it's audible. No issue.
Audible, sir.
Yeah. Our most respected Honorable Chairman, sir, Chief Guest Colonel B. Venkat, Registrar, Terry College of Advanced Studies, and former Director of Faculty Development, Cell AICTE, our Director, sir, Principal Dr. Venugopal, sir, Convener of this FDP, Co-Convener, faculties, and participants of this FDP. Good evening to one and all present here. It gives me immense pleasure in welcoming you all for the valedictory function of 6-day FDP program on AI and quantum computing, future of intelligent systems. At the outset, I would like to congratulate the organizers for choosing this topic. This topic is the latest topic under research which leads to the future. I hope all of you will be carrying a lot of information about AI and quantum computing through this FDP. I would like to share with you some of the applications of AI and quantum computers so that you will know the power of AI and quantum computing. As a first example, let us consider the Chandrayaan-3, in which the application of artificial intelligence was used in many ways. In that, let us consider the landing of the lander. AI was used to assist the lander in landing safely by predicting topography, identifying hazards, and managing the descent. Not only that, AI was used in the design, data analysis, and navigation of Chandrayaan-3. As a second application, okay, let us see the application of this AI in the medical field, which includes the drug delivery, drug discovery, personalized medicine, or that means a tailored medical care can be given to the patients, robotic surgery, clinical decisions making. Okay. AI can also assist clinicians with the treatment decisions, particularly in predicting therapy response. As a third application, okay, let us consider the defense sector. You know, in defense also AI has entered in the form of autonomous vehicles and robots, data management, training and simulations, cyber security, border surveillance, threat monitoring, lethal autonomous weapons systems. Another application also let us consider the application of AI in marine technology and underwater robotics. Also, in the advanced missile systems using AI technology is also considered where this AI is being employed. And we know that airplanes are being landed by using instrument landing system, ESC. Okay, now this AI is being used for landing. Okay, that is what all the landings are safe landings with the help of our AI. Or in a single sentence, I can say that wherever computers are available, AI has also entered in that field. Let me just throw a small light on this quantum computers also. Okay. In one sentence, I can able to say that in quantum computers, that might take a classical computer thousands of years to complete a particular task. can be reduced to a matter of minutes. That is the power of quantum computers. We know that all the experts throughout 6 days, they have given a lot of information regarding these quantum computers. So I hope that our participants will be bagging a lot of information regarding these quantum computers, which I may not be addressing about that. With this brief introduction, let me conclude my speech by welcoming you all to the validatory function of this 6-day FDP program on AI and quantum computing, future of these intelligent systems. Also, on behalf of the management, student, staff, and on my own behalf, I am welcoming you all once again to this validatory function. Welcome you all.
Thank you, Kannan sir. Uh, Thank you for your inspiring words and blissful speech. So we are honored deeply by the presence of Dr. Venugopal Kurnul, principal of Bharat Institute of Engineering and Technology. So your guidance and encouragement have been instrumental in creating a conducive environment for learning and growth. So let's welcome Dr. Venugopal Kurnul for his informative speech.
Yeah. Good evening to everyone. Am I audible, please? Hello.
Yes, sir. You're audible,
Good
sir.
evening. So first of all, I want to express my gratitude to the respected chairman for allowing us to do this program, in which so many participants have been participated, and they have learned various techniques of cutting edge technologies. And first of all, the respected chairman, participants, Atal FTP convener, speakers, I express my gratitude for having conducted this program in a manner that everyone feel very satisfied. At the end, I have also participated in the lecture. So people are very enthusiastic. They have raised their hands, still they raise their doubts, because this is a cutting edge technology. People have so many doubts about the data applications, data. This one, last time they have asked how to project the data, how to forecast the data, and data privacy, etc. So everything they are exposed to, because so many experts are there from IITs, from IIMs, and from IITs, then BITS Pilani, then DRDL, UTM Malaysia, Jellycare, and other private institutes. So this program is sponsored by AICTE and organized by Department of Electronics and Communication of BET Engineering College. In a week program, you have undergone training under cutting edge technologies of future. There are eminent speakers. We have also applications, because AI and ML is application in every domain nowadays. So I came from the background of water resources. So I was a director for groundwater department, where I used to apply regression analysis to forecast the groundwater levels in future based on the monsoon rainfall. And we used to identify the villages where there is going to be a water scarcity and where there is a transport of water to be made. It has made a lot of savings, because earlier what was happening is, wherever there is a political interference is there, they used to transport the water irrespective of whether there is water available there or whether water scarcity is there. Because of this application of regression analysis, we used to find out where there is water scarcity, where this transportation of water has to be deployed, and it has saved a lot of money to the government. And Chandrababu Naidu sir, he was very appreciative of our department for having deployed in a small measure this regression analysis to forecast the groundwater levels. So I come across many instances, many case studies in this program where people have applied AI and ML, and it has got a lot of future also. And there is no domain where AI and ML applications will not find a place. With this small this message, I want to conclude, and I also want to thank all the resource persons, speakers, for giving this excellent lectures on this quantum computing and other areas where there is a frontier technologies, and they are expanding, and they have got and it has got a lot of future, a lot of things in future, and applications also we find it in various domains. So I thank the organizers for given me this opportunity to interact with you in a small way, and because I also appreciate the AI and ML applications in various fields, because I myself applied in a small measure this regression analysis and saved a lot of money to the government. So with this small message, I want to conclude. Thank you once again for all the organizers for conducting the program in an excellent manner. Thank you very much, sir.
Thank you, sir. Thank you for your inspiring words. So, moving on next in the journey, I must express my profound gratitude to our chief guest, Colonel B. Venkat, Registrar of Terry School of Advanced Studies and a former director of AICTE. We are very grateful to you, sir, for taking out some time from your busy schedule and grace this occasion. So let's welcome Colonel B. Venkat, sir, for his inspiring speech.
Thank you. Thanks a lot.
Sir,
Surakshit,
just
thanks
a
a lot.
minute. Before that, I would like to read the profile of Colonel Venkat, sir. Though he's a very renowned person in when he was in AICT, we all know him, but still I would like to share the profile with the audience.
I'm with you. I'm with you. I think that can be done away with. Because thank you. Thanks a lot in any case, ma'am. It's so nice of you to have given me a chance to be interacting with the faculty members and scholars who are actually speaking, attending this. And compliments to the institute, compliments to Bharat Institute of Engineering and Technology, especially the Department of Electronics and Communication Engineering, for taking on a topic which is so very relevant. AI and quantum computing, be rest assured, I need not even sum it up by further saying that it's the future of intelligence system. It is the future which is going to be sustaining us or taking us in the times to come. And it's not only specifically that people from the engineering background or people specifically within the engineering only in electronics and communication to follow it. We have a wonderful education policy which cuts across all disciplines, and by saying with multidisciplinarity, where I am today, I have a university which is completely on humanities. And I see that each and every student is all the more eager to learn a subject of this nature when we talk about open electives. Each one of them is taking this particular topic, and this is the way it's going to move forward. And having said this, having said that the necessity of this cannot be undermined, compliments to each one of you, especially the organizers, especially Dr. Papya Datta, for taking it forward and making this subject so very pertinent. And in case if I heard correctly, participants in today's forum in this week-long schedule conducted in coordination with AICT was around 300. And that is something which speaks volumes of the manner in which this particular program has been conducted. By going through the speakers list as I was being introduced to the speakers when I was listening, the speakers were a very high profile professors, academicians, and industrialists who were from multiple disciplines but talking on the subject specific. And I only hope what the renowned people have spoken, each one of us who were present in the particular forum has made the best use of it. The idea for taking forward these kind of a week-long faculty development programs is basically to enhance your knowledge, to grasp something which is the best which is coming out of the particular week-long schedule, be in touch with the resource people, be in touch with each other, form some kind of an interactive group amongst yourself so that this topic continues and you derive the best from each other. So towards that, I think Bharat Institute of Engineering and Technology have done a wonderful work. And each one of the people who have participated, I think, shall benefit. And the benefit individually can only be welcomed or can only be appreciated in case the best what you have learned today is implemented at your workplace. The idea behind learning of this nature is how best now you can go back and give it back to the organization or give it back to your system. That is the genesis of these kind of things. Quite obviously, it enhances your personal knowledge, it enhances one's own personal gain. But the best part is when you give it back to the organization, and that is where you learn more, and that is where you contribute back to the system. Thanking you, thanks each one of you. And presently, I am tenanting the appointment as Registrar of Terry School of Advanced Studies. This is in New Delhi. which is the Energy Resource Institute, the erstwhile Tata Energy Resource Institute. Any one of you happening to come across New Delhi, anyone requiring any assistance, something, you're most welcome. I shall be more than happy to help each one of you, especially Bharat Institute of Engineering and Technology. I have been to your institute and I know the passion, I know the commitment that you people have. Keep it up, well done, and nothing can be said or more in a manner which is so very profoundly visible when you have a faculty development program having more than 300 people participating in it. Well done. All the best in your future endeavors. Thank you.
Thank you, sir. Thank you so much for your inspiration words. Shubhadip sir, please continue.
Yes, ma'am. So moving next, our participants do deserve commendation for their active engagement and constructive feedback. Your input reflects the true spirit of collaboration and ensures the continued success of initiatives like this. So I'd request any of the participants, if you're having any queries or if you want to share anything with us, you're most welcome. Okay, so I think we can move further. So finally, I would like to appreciate the efforts of Dr. Satyabrata Singha, the co-convener of this FDP, and I would also like to welcome him for delivering a heartfelt vote of thanks that encapsulates the spirit of
Okay,
gratitude
any
that we
participants
want
who
to
wants
share.
to give their feedback, please raise your hands. We are here to unmute you. In case, okay, fine, I got one. Jagad, okay, fine. Please, we are allowing you mic, sir. Please unmute yourself. Please unmute yourself. Your mic is allowed.
So good evening to one and all. Yeah, first of all, I would like to thank to AICTE for arranging this wonderful FDPs in online process, so that we can able to attend all these sessions. And this is the this is my third FDP. Yeah, this is where I enjoyed these sessions, all these sessions. They given a wonderful lecture on AI and machine learning also, and they introduced about the quantum computing. This is a new latest technology, so that will be impact in the future also. So that in that point of view, it is very useful to the research work also. And coming to the BIT, Bharat Institute of Technology, the coordinator, Datta Madam and Prasad sir also, they wonderfully they connected all these sessions very well. Thank to one and all for giving this opportunity. Thank you very much.
Thank you, sir. Any other participants who would like to share their feedback? They're most welcome. All right. So I think, Papia ma'am, we can continue further.
Yes, we can propose start the vote of thanks and end the program. Yeah.
So I would like to appreciate the efforts of Dr. Satyabrata Singha, the co-convener of this FDP, and I would also like to welcome him for delivering his heartfelt vote of thanks that encapsulates the spirit of gratitude that we all share. So let's welcome Dr. Singha.
Good evening, one and all. It is my privilege to deliver the vote of thanks as we come across the closing ceremony of 6 days online FTP on AI and quantum computing, the future of intelligent systems, under the ATAL initiative organized by Department of ECE, Bharat Institute of Engineering and Technology, Hyderabad. First and foremost, I extend my heartfelt gratitude to our chief guest for valedictory session, Colonel B. Venkat sir, Registrar of Terry School of Advanced Studies and former Director of AICTE, for gracing this program with the esteemed presence. Your inspiring words and encouragement have motivated all of us to continue striving for excellence in education and research. Special thanks to Dr. Anil Sahasrabudhe sir, Chairman of NATF, NBA and NAC, Mr. Sudhir Kumar sir, Director of Samsung R&D Institute, Bangalore, guest of honor and chief guest respectively for the inaugural sessions, for gracing this program with their presence and sharing their invaluable insights. We also express our sincere appreciation to Sri C.H. Venugopal Reddy sir, Honorable Chairman of BIT, for his unwavering support and guidance, without which the FDP would not have been possible. His vision continues to lead our institution towards excellence. A big thank you to Professor G. Kumaraswamy also, Director BIT, for his leadership and contributions, which have been instrumental in shaping this event and supporting our continuous growth. I would like to acknowledge Mr. Subhadip Goswami sir, Assistant Professor of BIT, for his invaluable technical assistance and hosting the event throughout, ensuring that everything ran smoothly throughout the FDP. A special note of thanks to Dr. Papia Dutta Madam, Associate Professor and convener of this FDP, for her tireless efforts in organizing and coordinating this event, making it a success from start to end. I also extend my sincere gratitude to Dr. V. Kannan sir, Dean of Administration at BIT, for his continuous support and for ensuring the smooth functioning of administrative aspect of this FDP. A heartfelt thanks to Dr. Venugopal Kundu sir, Principal of BIT, for his guiding us through the planning and execution of this FDP. I would also like to express our collective gratitude to all the esteemed speakers, Dr. Devasi sir, Dr. Sumandev, Mr. Sitaram Tarabali sir, Dr. Ivan Jayakumar, Mr. Vidyasagar Tejumurtula, Mr. Rohin Koduri, Dr. Ravina Kumar, Dr. Sivakumar Subramaniam, and Dr. Anish Chivukula, for their expert sessions on quantum computing, AI, data analytics, IoT, and more, and that has enriched our knowledge. And we sincerely appreciate the time and effort they have dedicated to this program. Finally, I extend my heartfelt thanks to all the participants. Your active engagement, enthusiasm, and insightful contributions have made this FDP a great success. And thank you for interaction after every sessions. We hope that the knowledge shared will inspire you to apply innovative ideas in your future work. To the organizing team, thank you for the seamless coordination and hard work throughout. So as we conclude this FDP, let us take forward the knowledge and inspiration gained over the past few days and continue to collaborate and innovate for a better future in education and research. Thank you once again, everyone, and I wish you all the best in the future endeavors. Have a wonderful evening. Thank you. Over to you, sir.
Thank you, Dr. Singha. So, as we conclude, let us not view this as an ending, but as a beginning, a stepping stone towards furthering our contributions to academia and society. Together, we can ensure that the knowledge and connections gained here will translate into meaningful outcomes for our students, institutions, and the larger educational landscape. So, participants, before we conclude this memorable valedictory session, let us take a moment to honor our nation and its values. So, I kindly request everyone to stand as we join together for the national anthem. Thank you.
Satya, sir, sound is not coming. Please check the sound. Please share it once again. Participants, please be there. After the national anthem, we will discuss about the assessment test and attendance once again because there is an update into that.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जगधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you, sir. Now, Dr. Papya Datta ma'am, convener of the FDP, will be giving you certain information regarding the assessment. Over to you, ma'am.
Yes, thank you, sir. Dear participants, a lot of queries are coming regarding the assessment test. Let me tell you that your assessment link will be on from 8:30 p.m. tonight. Okay, so it will be on till from 8:30 p.m. tonight. But once the attendance is uploaded completely, we are trying to upload the attendance since the morning, but the problem is AICT server is today very low. So you all know how the AICT server works. So as it is working very low, so very slowly we are able to upload the attendance. I think almost we have completed with out of 346, around 80 has been done, 80 to 100 has been done. Okay, so you can check your attendance. Once your attendance is completed for all 6 days, then only you will be getting the assessment link. And once you get the assessment link, it will you can start the test at 8:30 p.m. Okay, I suggest you to start the test. If you see the server is okay, fine, working, then you can do in the night, or else you can start in the morning also. So morning time will be till 12 o'clock or maybe till 1 o'clock maximum you can complete your test. Okay. So tomorrow by 1 o'clock you should complete your test. Once your test is completed, do fill the feedback form. There's a feedback form again in your dashboard. Just go to that feedback link and that in the dashboard and fill the feedback form. Once you complete the feedback form, then only you will be able to generate the certificate. Your certificate will be available in your own login. So with the names and designation that you have provided, it is nothing in our hands. So once the whole thing is completed, your attendance uploaded, assessment completed, feedback completed, then only you will be able to download the certificate. Okay. So I hope some of the participants we have uploaded the attendance, you can check it. But remaining we are doing slowly. So please give us some time because portal is very low, server is very low today. So yesterday the problem was not there, but today we are facing it. So slowly we are doing. Hopefully we'll complete it by tomorrow morning. Okay. So thank you all for the participation and wish you all best wishes for the future. And it was very nice of you all to join this FDP. Thank you once again.
Thank you, ma'am.
Ma'am.
Yeah, sure, sir.
Once the assessment is started, you have 45 minutes to complete it. Otherwise, it will be submitted automatically. That point, madam has not added, I think. So you have time till 12 o'clock tomorrow, but once the test is started, you have 45 minutes.
Some queries are there. You can unmute yourself. Asha, Priyadashini and Nupur. Yeah, please unmute yourself. Yeah, you can unmute yourself. Yes, Madam Nupur, you want to ask something?
No, ma'am.
Good evening, madam. Hello, madam.
Yes, sir, please. Rajkumar, sir, please, sir.
Tomorrow, most of the faculties are having the group 2 invitations, madam, to morning and afternoon sessions.
Okay, I understand. So afternoon, what time it will end?
Actually, morning up to 12:30
Okay.
and afternoon around 3 o'clock. So better to up to 2 o'clock you can able to enable the link, madam. Is
Okay,
it good?
actually from whatever the instruction we have received from AICTE is, it is 24 hours they have given the time slot after the starting of the examination. So 8 o'clock we have kept from our side the timing. So it is
Okay.
available till tomorrow 6, 7 o'clock it will be there. Okay, but I suggest as fast as you can complete it is better. Okay.
Okay, madam. Okay. Just to giving
Okay.
information only.
Yeah, 45 minutes is the time duration, 30 minutes, 30 questions are there. And question bank already we have shared. Once again, I'll put in the group.
Okay, madam. Thank you, madam.
Thank you,
Right.
sir.
Thank you for your good activity, madam.
Thank you, thank you. Okay, we are ending the meeting. In case of any queries, you can just DM me. Okay, fine.
Thank you, ma'am. Thank you all for making this FDP a grand success. May we continue to strive for excellence and innovation in all our endeavors, in fact, in all our future endeavors. So, wishing you all a safe and a pleasant evening. So, goodbye.
Okay, some more queries are there. I am unmuting yourself. Please, you can ask. Minal Bhute and already Rajkumar has told. Yeah. Miss Minal Bhute, you want to ask anything? Okay, we are ending the meeting then in that case.